Hey guys, welcome back. Tonight, I want to share a question that has stayed with me for a very long time. Not because anyone has answered it, but because no one has. 56 million years ago, something happened on this planet. Something powerful enough to change the climate, alter the oceans, and leave a chemical fingerprint buried deep inside the rocks beneath our feet. Scientists can measure it, they can see it. Not they can trace it across the entire Earth, but they still cannot fully explain what caused it. And the deeper I looked into the evidence, the more uncomfortable the question became. Because what if the most important clue in Earth's history is not what we found, but what disappeared? What if something was here before us? Not necessarily another humanity, not necessarily a forgotten civilization, but something that left a mark so profound that millions of years later we can still see its shadow without knowing what cast it. Tonight, I want to invite you to join me on a journey through ancient carbon, lost worlds, buried monuments, vanished coastlines, and mysteries that refuse to stay buried. We are not here to prove anything. We are here to follow the evidence, wherever it leads. So before you get comfortable, take a gentle moment to like this video and subscribe. But only if these deep sleep history stories help you find peace, sleep better, or simply reflect on our shared journey through time. Now, close your eyes, take a slow breath, and together, let's travel back 56 million years to a fingerprint in the stone that should not exist. The first time I encountered the Paleocene-Eocene thermal maximum, or PETM, it appeared to be just another ancient climate event buried somewhere in the vast timeline of Earth's history. At least, that's what I thought at first. Our planet has endured countless catastrophes over billions of years. Continents have collided and separated, oceans have opened and disappeared, entire groups of creatures have risen to dominance only to vanish forever. Against such an immense backdrop, one more climate event hardly seemed remarkable. But the more I read, the more I realize there was something different about this one. Something that refused to stay neatly contained inside textbooks and scientific papers. Something that kept pulling me back. 56 million years ago, long before the first human being took a breath, long before the first city, the first language, or the first memory, something extraordinary happened. The Earth suddenly experienced a massive disruption. Temperatures rose across the globe, oceans became warmer, ecosystems shifted, and the climate system was pushed far beyond its normal balance. None of that is controversial. Scientists have studied this event for decades. The evidence exists in sediment cores extracted from oceans around the world, preserved inside layers of ancient rock that have remained untouched for millions of years. What fascinated me was not the fact that the planet warmed, but the reason it warmed, or perhaps more accurately, the reason we still cannot fully explain why it warmed. As I dug deeper into the research, I discovered that the heart of the mystery lies in carbon. Not just carbon itself, but a specific type of carbon. When researchers examined the geological record from the beginning of the PETM, they found a dramatic shift in carbon chemistry, a signal so large, so sudden, and so widespread that it appeared almost everywhere scientists looked. In rocks from the Atlantic, the Pacific, the Indian Ocean, and even the Southern Ocean, the same fingerprint appeared. It was as if the entire planet had recorded the same event at precisely the same moment. I remember sitting quietly after reading one of those studies, imagining researchers drilling deep beneath the ocean floor, pulling up cylinders of ancient sediment, and discovering a message left behind by a world that no longer exists. Because that is what it felt like, a message. Not written in words, but in chemistry. Not carved into stone, but locked inside it. And the message said something extraordinary had happened. Estimates suggest that between 3 and 7 trillion tons of carbon entered Earth's atmosphere during the PETM. Even today, those numbers feel difficult to comprehend. Trillion is one of those words we use often, but rarely visualize. Imagine the entire industrial output of modern civilization. Factories, power stations, cargo ships, airplanes, automobiles, millions of machines operating across the globe. Then imagine multiplying that impact until the numbers become almost impossible to grasp. The carbon release associated with the PTM was enormous, enough to alter the entire climate system of the planet. Global temperatures rose by several degrees. Deep ocean environments became acidic. Many marine organisms struggled to survive. Entire ecosystems were forced to adapt, migrate, or disappear. And perhaps most astonishing of all, the Earth required nearly 200,000 years to recover. 200,000 years, a span longer than the history of our own species. That detail stayed with me. Whatever happened, whatever pushed the climate so far out of equilibrium, its effects lingered for a period greater than the entire existence of Homo sapiens. That is not a minor disturbance. That is a planetary transformation. Yet, the deeper I looked, the stranger the story became. Because scientists were able to identify something incredibly specific about the carbon involved. Carbon exists in different isotopic forms, primarily carbon-12 and carbon-13. Living organisms tend to favor the lighter version. Carbon-12, plants absorb it, animals consume it, and over time, biological material becomes enriched with this lighter isotope. As a result, anything that originates from living matter carries a recognizable chemical signature. Fossil fuels carry it, ancient forests carry it, organic sediments carry it. And when researchers examined the PTM signal, they found precisely that fingerprint. Not just carbon, but biologically derived carbon. Carbon that once belonged to living systems. That discovery transformed the mystery, because suddenly the question was no longer simply, why did the climate change? The question became, where did all that biological carbon come from? What source on Earth could release such staggering quantities of carbon into the atmosphere over such a short period of geological time? Every answer seemed to create new questions. Scientists proposed volcanic activity, methane hydrates beneath the seafloor, vast stores of ancient organic matter heated by geological processes. Many of these explanations likely contributed to the event. Yet again and again, as I moved through paper after paper, I encountered the same quiet admission hidden within the technical language. The models did not completely balance. The numbers came close, but not close enough. There remained a gap, a discrepancy, a missing piece that 30 years of research had not fully eliminated. And that was the moment the PEM stopped feeling like an ancient climate event and started feeling like a mystery. Not because the science was weak, but because the science was so strong. The evidence was everywhere. The fingerprint was clear. The event was real. And yet, one crucial question remained open. Something released an immense amount of biologically derived carbon into Earth's atmosphere 56 million years ago. Something altered the climate of an entire planet. Something left behind a chemical signature so powerful that it can still be measured today. We know the fingerprint exists. We know when it appeared. We know what it did to the world. But the deeper I followed the evidence, the more I found myself staring at the same uncomfortable thought. We still do not know exactly what left that fingerprint behind. The more I learned about the PM, the less it felt like a story about climate, and the more it felt like a story about evidence, not the kind of evidence that appears in museums or the kind displayed behind glass cases under bright lights. This evidence existed at a scale so small that it could only be seen through instruments, hidden inside atoms, preserved within the chemistry of ancient rock. And strangely enough, that tiny detail became the very thing that made the mystery impossible for me to ignore. At the center of it all was carbon, the same element found in every tree, every animal, every ocean, and every human being alive today. Carbon is the foundation of life as we know it. But what fascinated me was that carbon is not completely uniform. It comes in different forms, known as isotopes. To most people, the difference sounds insignificant. Carbon-12, carbon-13, just numbers attached to the same element. Yet those numbers tell stories, stories that stretch across millions of years, stories hidden beneath the surface of the Earth. Carbon-12 is slightly lighter than carbon-13. The difference is only a single neutron, something so small that it seems almost meaningless, but life notices the difference. Plants, through the process of photosynthesis, preferentially absorb carbon-12, Animals then consume those plants, carrying the same signature through entire ecosystems. Over vast spans of time, forests, soils, microorganisms, and every living thing become enriched with the lighter isotope. It is one of those remarkable details about nature that feels almost invisible until someone points it out. Then suddenly, it seems obvious. Life leaves a fingerprint, a chemical preference, a pattern. And once you know how to recognize that pattern, you can begin reading the history of the planet in a completely different way. I remember the moment I first understood why scientists care so much about carbon isotopes. It felt like discovering that ancient rocks could speak, not with words, but with ratios. Every layer of sediment, every shell buried beneath the ocean floor. Every piece of limestone contains a record of the carbon that existed when it formed. Millions of years later, researchers can measure those isotopes and reconstruct events that no human ever witnessed. It is almost like reading pages from a diary written by the Earth itself. And when scientists examined the rocks from the beginning of the PPTM, they found something astonishing. The carbon signal shifted dramatically toward carbon 12. Not slightly, dramatically. The geological record showed a sudden flood of biologically derived carbon entering the atmosphere and oceans. The fingerprint was unmistakable. It was the same signature associated with organic material, with ancient forests, with fossil fuels, with carbon that had once passed through living systems. That was the point where my curiosity began turning into suspicion, because the signal looked strangely familiar. Today, when we burn coal, oil, and natural gas, we release carbon that originated from ancient life. Those fuels are essentially compressed biological material, stored underground for millions of years before being extracted and consumed. As a result, modern industrial emissions carry the same isotopic fingerprint, an enrichment of carbon 12. Scientists can see that fingerprint in the atmosphere right now. They can measure it year after year, praises. It is one of the clearest indicators that fossil fuel combustion is altering the chemistry of the planet. But then I encountered something that stopped me in my tracks. The PETM fingerprint looked remarkably similar. Not identical in every detail, but similar enough to raise questions. 56 million years ago, an enormous amount of biologically derived carbon entered the atmosphere. Today, an enormous amount of biologically derived carbon is entering the atmosphere. The comparison was impossible to ignore. Of course, similarity does not mean equivalence. Similar fingerprints can emerge from different processes. Scientists are careful about this distinction, and rightly so. But I found myself asking a question that lingered in the back of my mind. If the chemical signature symbols the release of stored biological carbon, where exactly did that carbon come from? The standard explanations offer possibilities. Massive methane deposits trapped beneath ancient oceans, organic-rich sediments heated by volcanic intrusions, feedback loops that amplified initial warming and released additional carbon. These mechanisms are real, and they likely played important roles. Yet, as I continued reading the literature, I kept encountering cautious language. Researchers described uncertainties. They discussed assumptions. They noted that some models required larger reservoirs than those currently documented. Others depended on chains of events that were difficult to verify directly. The explanations were plausible, but there was always an uncomfortable sense that the story remained incomplete. It reminded me of listening to someone describe a crime scene while one crucial piece of evidence remained missing. The outline made sense, but the details refused to settle into place. And the deeper I looked, the more often I encountered the same phrase expressed in different ways. Additional carbon sources may have been involved. Additional mechanisms may be required. Further research is needed. Those words appear frequently in science, and usually they are unremarkable. But here, after decades of investigation, they carried a different weight. Because the PM is not some obscure geological event studied by a handful of specialists. It is one of the most researched climate disruptions in Earth's history. Thousands of papers have examined it. Generations of scientists have analyzed it. Yet the question remained, where did all the carbon come from? I remember sitting quietly one evening after reading another technical paper, staring at a graph showing the carbon isotope excursion. a sharp plunge recorded in ancient sediment, visible across multiple oceans preserved for 56 million years. The signal was real. The fingerprint was real. And suddenly I realized what bothered me most. It was not the possibility that scientists lacked an answer. Science is filled with unanswered questions. What bothered me was how clear the fingerprint seemed to be and how uncertain the source remained. Imagine finding a footprint in fresh snow, seeing every detail of the shoe, every ridge, every pattern, and yet having no idea who left it. That was how the PTM began to feel. We could see the fingerprint, we could measure it, we could trace it across the planet. We knew it pointed toward biologically derived carbon. We knew it resembled the signature associated with fossil fuels and ancient organic matter. Yet the identity of the source remained frustratingly elusive. And somewhere during that realization, I felt my perspective begin to change. I was no longer reading about a climate event. I was reading about a mystery written in carbon, preserved in stone, waiting patiently for someone to explain the fingerprint that should have answered everything, but somehow answered nothing at all. After realizing that the carbon carried a biological fingerprint, I naturally assumed that scientists must have already identified the source. After all, if the evidence was so clear, if researchers had spent decades studying one of the most dramatic climate disruptions in Earth's history, surely the mystery had already been solved. But the deeper I went into the literature, the more surprising the situation became. The truth was not that scientists lacked explanations. Quite the opposite. They had several explanations, each supported by evidence, each capable of accounting for part of the story. The problem was that none of them seemed capable of accounting for all of it, and that was where the mystery truly began. The first explanation involved volcanoes. At roughly the same time as the PETM, enormous volcanic activity was occurring in the region that would eventually become the North Atlantic. The ancient continents were pulling apart, opening the ocean basin between Greenland and Europe and generating vast amounts of magma. On the surface, this seemed promising. Volcanoes release carbon dioxide. Large volcanic provinces have altered climate before. Some of the greatest extinction events in Earth's history are linked to massive eruptions. For a while, I thought the answer might be that simple. Perhaps volcanoes had simply flooded the atmosphere with carbon. But then I learned about isotopes. The carbon emerging from deep within the Earth carries a different signature than carbon originating from biological sources. Mantle-derived carbon tends to contain relatively higher proportions of carbon-13. The PETM signal, however, was dominated by carbon-12. The fingerprint did not match. Volcanic activity may have contributed to warming, perhaps even triggering other processes, but it could not fully explain the isotopic anomaly preserved in the rocks. The fingerprint pointed elsewhere. So researchers turned their attention toward another possibility: methane hydrates. The idea is fascinating. Deep beneath the ocean floor, enormous quantities of methane can become trapped inside crystalline structures of ice. These frozen deposits remain stable under conditions of high pressure and low temperature. For millions of years, they can sit quietly beneath the seabed, storing vast amounts of carbon. But if ocean temperatures rise, those deposits can destabilize. Methane escapes. Once released, methane becomes a powerful greenhouse gas capable of amplifying warming even further. What made this hypothesis particularly attractive was the chemistry. Methane generated by biological processes carries the same light carbon signature seen during the PETM. The fingerprint matched, the timing seemed plausible, the feedback mechanisms made sense. I remember thinking, perhaps this was finally the answer. Yet once again, the numbers became a problem. Scientists began estimating how much methane could realistically have been stored in ancient hydrate reservoirs. They built increasingly sophisticated models, reconstructed ancient ocean temperatures, and calculated potential release volumes. Again and again, they reached a similar conclusion. Methane hydrates likely contributed significantly, perhaps even dramatically, but the total amount of carbon they could supply appeared insufficient. The models came close, but not close enough. There remained a gap between the carbon required by the geological record and the carbon available from known methane reservoirs. The mystery persisted. Then came a third explanation, one that initially sounded less dramatic but quickly became equally intriguing. Organic rich sediments. Throughout Earth's history, vast quantities of biological material have accumulated within sedimentary layers. Ancient forests, microorganisms, marine organisms, entire ecosystems can become buried and compressed beneath younger deposits. If magma intrudes into these carbon-rich layers, the heat can effectively cook the organic material, releasing carbon dioxide and methane into the atmosphere. This mechanism seemed almost tailor-made for the PETM. The volcanic activity associated with the opening North Atlantic could have heated enormous sedimentary deposits. Those deposits contained biological carbon. The resulting emissions would carry the correct isotopic signature. Once again, the chemistry appeared promising. Once again, the mechanism seemed plausible. And once again, the models struggled. Researchers found that thermal decomposition of organic sediments likely contributed substantial amounts of carbon, perhaps enough to explain a significant fraction of the event. But even after including these emissions, many reconstructions still fell short of the total carbon recorded in the geological record. That phrase kept appearing. Fell short, not wildly wrong, uh, not completely impossible, just insufficient. A little too little carbon, a little too much uncertainty, a little too much dependence on assumptions. Individually, each explanation accounted for part of the puzzle. Together, they came much closer. Volcanoes may have initiated warming, methane, hydrates may have amplified it, organic sediments may have supplied additional carbon. The combined picture became increasingly sophisticated. Yet as I continued reading, I could not shake a simple observation. 30 years of research had not produced a universally accepted solution. Scientists were not arguing over tiny details. They were still debating the fundamental source of one of the largest carbon releases in Earth's history. The more papers I read, the more frequently I encountered careful scientific language. Additional carbon sources may have existed. Reservoir sizes remain uncertain. Model sensitivity affects outcomes. Feedback mechanisms require further study. These phrases appeared again and again, not because researchers were careless, but because they were honest. They were acknowledging the limitations of current understanding. And strangely enough, that honesty made the mystery even more compelling. Because the PM is not an obscure anomaly buried in some forgotten corner of geology. It is one of the most intensely studied climate events on Earth. Thousands of scientists have examined it. Vast amounts of data have been collected. Entire careers have been devoted to understanding it. Yet, despite all of that effort, despite decades of research, the books still do not quite balance. I remember looking at a summary graph from one study, watching colored bars represent different carbon sources. Volcanoes, methane hydrates, organic sediments, each contributed a portion. Each moved the explanation closer to completion. Yet there remained a blank space at the end, a remainder, a missing quantity. Not enormous, but significant enough that researchers could not ignore it. And that was the moment something changed in the way I thought about the PETM. Before, I had viewed it as a solved event with unresolved details. Now, I began to see it as an unresolved event hidden inside a solved framework. We know what happened. We know temperatures rose. We know oceans acidified. We know biological carbon flooded the atmosphere. We know the fingerprint exists. What remains uncertain is the source. And after 30 years of investigation, that uncertainty has proven remarkably resilient. The deeper I looked, the more I felt drawn toward a question that seemed almost impossible to ignore. If every major explanation accounts for part of the evidence, yet none fully accounts for all of it? What if the missing carbon is not simply a calculation problem? What if the gap itself is trying to tell us something? That thought lingered quietly in the back of my mind, and before long, it would lead me toward a paper that asked one of the most unusual scientific questions I have ever encountered. By this point, I should probably tell you something. The reason the PEM stayed with me was never because of what scientists know. It was because of what they do not know. That may sound like a strange thing to say, especially when discussing one of the most thoroughly studied climate events in Earth's history. We often assume that the accumulation of knowledge gradually eliminates mystery. The more data we collect, the smaller the unknown becomes. Usually, that is true. But every now and then, a different situation emerges. Sometimes the data becomes stronger, more precise, more detailed, and yet the central question remains stubbornly unanswered. The PETM felt like one of those cases. The fingerprint was there, the climate disruption was there, the carbon was there, the geological record was there, and yet, after decades of investigation, something still refused to fit. I found myself returning to that thought again and again, not because I believed some hidden answer was waiting around the corner, but because the gap itself seemed unusually persistent. Think about what normally happens in science. Researchers identify a problem, gather evidence, test competing explanations, refine their models, and gradually move closer to consensus. It is not a perfect process, but it works remarkably well. Yet with the PETM, even after 30 years of intense study, scientists were still discussing missing carbon sources, uncertain reservoir sizes, unresolved feedback mechanisms, and unexplained discrepancies between models and observations. The event was not poorly understood, far from it. In many ways, it was understood extraordinarily well, which somehow made the remaining uncertainty even more difficult to ignore. The more papers I read, the more I began noticing a pattern. Every explanation seemed capable of accounting for part of the evidence, but none seemed entirely comfortable carrying the full weight of the story. Volcanoes contributed, but not enough. Methane hydrates contributed, but perhaps not enough. Organic sediments contributed, but still the numbers often struggled to close completely. Researchers adjusted assumptions, revised models, incorporated new data, and narrowed the uncertainties. Yet the gap never seemed to disappear entirely. It remained quietly sitting there in the background, not large enough to invalidate the science, but significant enough to keep the discussion alive. And that was the point where I started asking myself an uncomfortable question. What if we were looking at the problem from the wrong direction? Not because the science was wrong, but because the framing of the question itself might be incomplete. After all, when a mystery persists for decades, despite enormous amounts of data, it sometimes suggests that an assumption hidden within the investigation deserves another look. I am not talking about abandoning evidence. Quite the opposite. I am talking about following the evidence wherever it leads, even when it leads somewhere unexpected. The thought first appeared almost accidentally. I was reading yet another discussion about carbon reservoirs, tracing estimates and uncertainties, when I realized something peculiar. Nearly every explanation began with the same assumption. The source had to fit within known natural mechanisms, and of course, that assumption made perfect sense. Science naturally prefers explanations grounded in established processes. Volcanoes exist, methane hydrates exist, organic sediments exist. These mechanisms are real, measurable, observable. But I found myself wondering whether the question itself had become constrained by familiarity. What if there were aspects of Earth's history that left evidence we recognize, but origins we do not? What if certain events survive in the geological record while the processes that created them disappear? That thought lingered longer than I expected. The deeper I reflected on it, the more fascinating the implications became. Imagine discovering a footprint preserved in stone, perfectly visible after millions of years, while everything associated with the creature that made it has vanished. No bones, no skin, no traces of its environment, only the footprint remains. You would know something passed that way. You would know approximately when it happened. But understanding exactly what left the mark could become extraordinarily difficult. In some ways, the PM felt similar. The fingerprint survived. The consequences survived. The chemistry survived. Yet the origin remained strangely elusive. I remember one evening sitting alone with several scientific papers spread across my desk, staring at graphs showing carbon isotope excursions. There was something almost haunting about them. A sudden shift, recorded across oceans, preserved for 56 million years, visible to anyone with the right instruments. It felt less like data and more like an echo from a world so distant that no direct witness could ever exist. And yet, The signal remained strong enough to reach us across unimaginable stretches of time. That realization changed how I viewed the mystery. The PEM stopped feeling like a problem waiting to be solved and started feeling like a question waiting to be asked correctly. Because perhaps the most important discoveries are not always found by collecting more evidence. Sometimes they emerge when someone looks at familiar evidence and asks a different question. What if the missing carbon is not the mystery? What if the mystery is why we assume the source must fit neatly within the explanations we already know? I am not suggesting an answer. At this stage, I did not have one. What fascinated me was the existence of the question itself. The fact that after 30 years, despite extraordinary scientific effort, a small but persistent uncertainty remained embedded within one of the most important climate events ever studied. And once that thought took hold, I found it impossible to let go. Because if there was even a chance that we were asking the wrong question, then the story of the PETM might be far stranger than anyone imagined. It might not simply be a story about carbon or climate or geology. It might be a story about the limits of what survives, the limits of what evidence can tell us, and the unsettling possibility that sometimes, even when a fingerprint remains perfectly preserved, the identity of whatever left it behind may vanish almost completely. That was the question that refused to die, and soon it would lead me toward a scientific paper that asked something so unusual, so unexpected, that I initially thought I had misunderstood the title. Yet, the more I read, the more I realized it might be asking exactly the question I could no longer ignore. For almost 30 years, the PTM sat quietly inside the scientific literature, not hidden, not ignored, but never fully explained. The data was clear. The fingerprint was clear. The carbon was real. The climate disruption was real. Yet the gap remained. Every proposed mechanism contributed to something, but none seemed capable of closing the books completely. And if the story had ended there, it would still have been one of the most fascinating mysteries in Earth science. But in 2018, something happened that changed the way I thought about the entire problem. It began with a paper, not a sensational book, not a television documentary, not a fringe theory circulating on obscure websites, a formal scientific paper published in a peer-reviewed journal. I still remember the first time I saw the title. At first, I thought it had to be a joke. The title sounded almost absurd, almost impossible. Yet the names attached to it were impossible to dismiss. One of them was Gavin Schmidt, a climate scientist associated with NASA and director of the Goddard Institute for Space Studies. The other was Adam Frank, an astrophysicist at the University of Rochester. Neither man was known for promoting extraordinary claims. Neither had a reputation for pseudoscience. Both had spent decades working within the scientific mainstream, which made the paper all the more surprising, because the question they chose to ask was unlike anything I had ever encountered in a scientific journal. Not because it was outrageous, but because it was so simple, so obvious, and yet so rarely discussed. The paper was called The Silurian Hypothesis. The name itself came from an old science fiction reference, a nod to a species from Doctor Who said to have inhabited Earth before humans. But the paper was not about science fiction. It was about geology, about evidence, about time, and most importantly, about what survives. Schmidt and Frank did not claim that an ancient industrial civilization had existed. They did not argue that lost empires once ruled the earth millions of years ago. They did not present evidence for forgotten cities, vanished technologies, or prehistoric machines. In fact, they did the opposite. They began with a question, a purely scientific question. If a civilization comparable to our own had existed tens of millions of years ago, would we even know? The moment I read that sentence, something clicked, because I realized they were not asking whether such a civilization existed. They were asking whether the geological record was capable of detecting one. And those are two very different questions. Most discussions about ancient civilizations begin with assumptions. They start with monuments, myths, artifacts, legends. The Silurian hypothesis started somewhere else entirely. It started with physics, chemistry, erosion, plate tectonics, deep time. Schmidt and Frank approached the problem methodically. Imagine, they said, a civilization similar to ours, a civilization capable of industry, capable of altering its environment, capable of extracting resources and releasing carbon into the atmosphere. Now imagine that civilization disappeared, not thousands of years ago, not tens of thousands, but tens of millions of years ago. What would remain? At first, the answer seems obvious: buildings, roads, foundations, artifacts. Yet the more I thought about it, the less convincing those answers became. 50 million years is an incomprehensible amount of time. Continents move, mountains rise and erode, oceans open and close. Entire landscapes vanish beneath sediment. The surface of the earth is constantly recycled. Geological time is relentless. Schmidt and Frank calculated what would survive such immense spans of time. The results were unsettling. Cities would disappear. Concrete would disappear. Steel would oxidize and vanish. Plastics would break down. Landfills would become unrecognizable. Roads would be erased. Buildings would collapse. Weather, and eventually become indistinguishable from ordinary geological deposits. Even many isotopes associated with nuclear technology would decay beyond recognition. The Earth would consume nearly everything. The physical evidence of civilization, the things we imagine as permanent, would be gone, completely gone. But not everything would disappear. One category of evidence would remain: chemistry. Isotope ratios, trace signatures embedded in rock, changes recorded in sediments deposited across oceans. In other words, the very kind of evidence we had been discussing throughout the PETM. And that was the moment the paper became impossible for me to forget, because Schmidt and Frank reached a conclusion that felt both obvious and disturbing. If an industrial civilization had existed millions of years ago, the geological record would not necessarily identify it as a civilization. It would identify it as a geochemical event. It would appear as a sudden anomaly in carbon, a strange shift in isotopes, an unusual concentration of trace elements, a disruption recorded in stone. It would receive a name. It would receive a date. Scientists would study it extensively. Papers would be published. Models would be developed. And the question of what caused it might remain officially unresolved. I remember staring at that conclusion for several minutes. Not because it proved anything, but because it changed the nature of the question. Suddenly, I was no longer asking whether an ancient civilization existed. I was asking whether the geological record itself could distinguish between an unknown industrial event and an unknown natural event. And the answer, according to the analysis, was surprisingly uncertain. The evidence could look remarkably similar. A civilization burns through stored carbon. The atmosphere changes. Oceans record the signal. Sediments preserve it. Millions of years later, only the chemical fingerprint remains. The city is gone. The machines are gone. The civilization is gone. But the carbon signal survives. The fingerprint survives. The record survives. And that was when I found myself returning to the PTM once again. A biological carbon signature. A massive carbon release. A volume that remains difficult to explain fully through known natural mechanisms. A mystery preserved in stone for 56 million years. I'm not saying the PTM was caused by a civilization. Schmidt and Frank never said that either. What they demonstrated was something far more subtle, and perhaps more important. They demonstrated that if such a thing had happened, the evidence might look exactly like the kind of geological mystery we already study today. That realization stayed with me long after I finished reading the paper, because for the first time, the question no longer sounded absurd. It sounded scientific. It sounded testable. It sounded like the kind of question that should be investigated rather than dismissed. And perhaps that was the most surprising part of all. Not the possibility itself, but the fact that so few people seemed willing to ask it. Once I understood the central idea behind the Silurian hypothesis, I found myself asking a question that felt almost embarrassingly simple. If an industrial civilization had existed 50 million years ago, where would it be? Where would the cities be, the roads, the factories, the machines, the evidence? Surely something would remain. Surely a civilization capable of altering the planet would leave behind traces impossible to erase. At least, that was what I assumed. But the more I investigated the question, the more surprising the answer became. Because the truth is that we tend to underestimate geological time. We think in years, decades, perhaps centuries. Occasionally, we stretch our imagination to thousands of years. Ancient Egypt feels unimaginably old. The Roman Empire feels distant. Even the last ice age seems almost beyond comprehension. But 50 million years belongs to an entirely different category of time. It is not merely longer, it is so vast that many of the processes we consider permanent become temporary. Mountains disappear, oceans move, continents drift, entire landscapes are erased and rewritten. The Earth is not a static archive, it is an active machine, a machine that constantly destroys its own history. I remember looking at satellite maps of the modern world and imagining every city on Earth suddenly abandoned. New York, London, Tokyo, Shanghai, Paris, Sao Paulo, Cairo. Imagine all human activity stopping tomorrow. No maintenance, no repairs, no protection from weather. Within decades, vegetation would begin reclaiming roads. Concrete would crack, metal structures would corrode, glass would shatter. Within centuries, buildings would collapse. Within thousands of years, many cities would become difficult to recognize. Within tens of thousands of years, entire regions could disappear beneath soil, forests, sediment, and changing coastlines. And that is only a tiny fraction of 50 million years. The deeper I explored the science, the more astonishing the implications became. Much of Earth's surface is constantly recycled. Wind erodes mountains, rivers transport sediment, oceans bury entire landscapes beneath new layers of mud and sand. Tectonic plates slowly slide beneath one another, carrying ancient surfaces into the mantle where they are eventually destroyed. The crust itself is temporary. In fact, almost no exposed surface on Earth survives unchanged for tens of millions of years. The overwhelming majority of ancient landscapes are gone, completely gone, which means that even if a city had existed 50 million years ago, the probability of finding it today would be extraordinarily small. The city would not simply decay, it would vanish. Every street, every foundation, every wall, every monument, consumed by geological processes operating patiently over immense spans of time. Then I began thinking about factories. Surely industrial facilities would survive longer. Massive steel structures, power plants, refineries, enormous complexes built from durable materials. Yet once again, geological time changes the equation. Steel rusts, aluminum corrodes, concrete fractures, water infiltrates everything, freeze-thaw cycles weaken foundations. Chemical weathering slowly dissolves exposed surfaces. Over millions of years, the distinction between a factory and an ordinary rock formation becomes increasingly difficult to preserve. Eventually, even the largest industrial structures would be reduced to fragments, and then those fragments would be recycled into sediments, buried beneath younger deposits, or destroyed altogether. What surprised me most was that this process is not hypothetical. We already see it happening. Ancient structures only a few thousand years old require constant excavation and preservation. Without deliberate maintenance, history disappears remarkably quickly. Extend those processes across 50 million years, and almost nothing recognizable remains. Then there was plastic. If there is one material people often assume will survive forever, it is plastic. Modern discussions frequently describe plastic as immortal, a permanent scar on the environment. In human terms, that description is understandable. Plastics can persist for decades, centuries, perhaps even longer under certain conditions. But geological time is merciless. Exposure to heat, pressure, ultraviolet radiation, oxidation, and microbial activity gradually breaks plastics down. Given enough time, they fragment, transform, and ultimately lose the characteristics that once made them identifiable. 50 million years is more than enough time to erase nearly every plastic object ever produced. That realization was strangely unsettling. We often imagine our civilization leaving behind mountains of artifacts, skyscrapers, satellites, vehicles, electronics, plastics. Yet when viewed through the lens of deep time, most of those objects become temporary, fleeting, fragile. The physical world we have built feels permanent because our lives are short. Geological time reveals a different perspective. It reveals how little survives. And that was the moment I finally understood why Schmidt and Frank focused so heavily on chemistry. Because chemistry behaves differently. A building can disappear, but the carbon released during its construction may remain recorded in sediments. A factory can vanish, but the atmospheric changes it produced may survive as isotope anomalies. A civilization can disappear, yet the chemical consequences of its activities may remain embedded in rock for tens of millions of years. The physical evidence dies, the chemical evidence persists. That distinction changed everything. Suddenly, the geological record looked less like a museum and more like a forensic archive, an archive that preserves effects rather than causes, consequences rather than objects, fingerprints rather than fingerprints owners. And once I saw it that way, it began to look different. We had been searching for physical evidence, cities, monuments, structures, things that would obviously reveal themselves as products of intelligence. Yet perhaps those were precisely the wrong things to search for, because after 50 million years, they would almost certainly be gone. What survives is chemistry, carbon ratios, isotope shifts, trace element anomalies, global signals recorded simultaneously across oceans and continents. Those are the things that endure. Those are the things geology remembers. Everything else fades away. The city disappears. The factory disappears. The plastic disappears. The machines disappear. The civilization disappears. And all that remains, buried beneath layers of stone, is a chemical fingerprint, a signal, an anomaly, a clue. The kind of clue scientists encounter all the time, the kind of clue that can be measured, analyzed, debated, and modeled, the kind of clue that may reveal that something extraordinary happened without ever revealing exactly what it was. And the more I thought about that possibility, the more I realized how profoundly it changes the question. Perhaps the real mystery is not whether evidence exists. Perhaps the real mystery is whether we would recognize the evidence if it were already sitting in front of us. The idea that stayed with me longer than anything else in the Silurian hypothesis was not the possibility of an ancient civilization. It was something far stranger, something that initially seemed almost impossible to accept. If a technological civilization had existed tens of millions of years ago, the geological record might not identify it as a civilization at all. Instead, it might classify it as a natural event. The first time I encountered that argument, I stopped reading and simply stared at the page, because the implication was profound. We tend to imagine civilizations leaving obvious evidence: monuments, machines, artifacts. We expect intelligence to announce itself. We expect cities to look different from mountains, factories to look different from volcanoes, industry to look different from nature. Yet deep time changes everything. Deep time strips away context. It erases intention. It removes the distinction between what was designed and what simply happened. What remains is not the thing itself, but its consequences. And consequences can be surprisingly difficult to interpret. Imagine for a moment that humanity disappeared tomorrow. Not next century, not after a slow decline, but suddenly. The cities are abandoned, the factories fall silent, the electrical grids fail, nature begins reclaiming the world. Thousands of years pass, then millions. Eventually, almost every physical structure vanishes. The skyscrapers collapse, roads disappear beneath sediment, dams erode, satellites fall from orbit. The visible evidence of civilization fades away, but some things remain. Atmospheric carbon changes, nitrogen cycles shift, certain metals become unusually concentrated in geological deposits, synthetic compounds leave chemical residues, ocean sediments preserve traces of environmental disruption. Future scientists, millions of years later, might discover these signals. They would see the consequences, but would they recognize the cause? That question haunted me, because once you ask it, you begin seeing geological history differently. The Earth contains countless anomalies: strange carbon excursions, sudden climate shifts, abrupt changes in biodiversity, layers rich in unusual elements, signals that appear globally and then disappear. Most of these anomalies eventually receive explanations, and many explanations are undoubtedly correct. But the Silurian hypothesis forces us to consider something unusual. What if some events are difficult to interpret not because the evidence is weak, but because the evidence is incomplete? What if we are looking at fingerprints without knowing who left them? The shocking aspect of the hypothesis was not that an ancient civilization existed. Again, Schmidt and Frank never claimed that. The shocking aspect was the realization that geology is not designed to identify civilizations, Geology identifies processes, it records outcomes, it preserves chemical transformations. When scientists analyze ancient rocks, they see carbon signatures, isotope ratios, sedimentation patterns, temperature changes, extinction events. These observations are real, they are measurable, they are extraordinarily valuable, but none of them inherently reveal intent. A geological layer cannot tell us whether carbon entered the atmosphere because of volcanic eruptions, methane releases, biological feedback loops, or industrial activity. It only records that the carbon arrived. The fingerprint remains. The source becomes the mystery. The more I thought about this, the more unsettling it became, because civilization itself is surprisingly small when viewed against planetary history. Humanity feels enormous because we live inside it. Our cities cover continents. Our technology connects billions of people. Our influence reaches every ecosystem on Earth. Yet, compared to geological processes, our existence is astonishingly brief. Modern industrial civilization has existed for only a few centuries. Geological events often unfold across thousands, tens of thousands, or millions of years. We occupy a tiny sliver of the timeline, a blink, a moment, a thin layer that future geology may struggle to interpret. And if that is true for us, what does it imply about the distant past? Suppose a civilization existed 50 million years ago, not necessarily human, not necessarily identical to ours, merely technological enough to alter its environment. What would it leave behind? The answer becomes surprisingly limited. Carbon anomalies, isotope shifts, trace metals, synthetic molecules, if any survived, climate disruptions, environmental disturbances recorded in sediments. In other words, exactly the kinds of evidence geologists already study every day. The city itself disappears. The roads disappear. The factories disappear. The civilization disappears. Only the chemical shadow remains. That phrase kept returning to my mind, chemical shadow, because it perfectly captured the essence of the problem. Geology does not preserve civilizations. It preserves shadows cast by civilizations. And shadows can be remarkably difficult to identify once the object creating them has vanished. Consider a simple example. If future scientists discovered a sudden carbon isotope excursion in rocks 50 million years from now, they might correctly conclude that large quantities of biologically derived carbon entered the atmosphere. They could measure the magnitude, estimate the timing, reconstruct the environmental consequences, yet without additional context. Uh, Distinguishing industrial emissions from certain natural processes could prove extraordinarily difficult. The signal itself would survive, the explanation might not. And suddenly, the PTM looked different to me, not because it became evidence of anything extraordinary, but because it demonstrated how little information a fingerprint actually contains. We know something happened. We know the carbon entered the atmosphere. We know the climate responded. We know ecosystems changed. But the fingerprint alone does not tell us why. The fingerprint tells us that an event occurred. Interpretation comes later, assumptions come later, models come later, and sometimes those interpretations remain uncertain for decades. That realization fundamentally changed how I viewed the geological record. Instead of seeing it as a complete archive, I began seeing it as a fragmented one, a record filled with clues but missing context. A record capable of revealing effects while concealing causes. A record that remembers consequences long after intentions have vanished. And perhaps that is why the Silurian hypothesis continues to provoke such strong reactions. Not because it proves anything, but because it exposes a limitation we rarely consider. It reminds us that geology can tell us what happened, yet sometimes struggle to tell us exactly why. It reminds us that evidence survives unevenly. And most importantly, it forces us to confront a deeply uncomfortable possibility. If a technological civilization ever vanished deep in Earth's past, the geological record might preserve its fingerprint while completely forgetting its name. After spending so much time thinking about the Silurian hypothesis, I found myself returning to the PETM once again, not because the hypothesis provided an answer, but because it changed the way I looked at the evidence. The rocks had not changed, the isotope ratios had not changed, the carbon fingerprint remained exactly the same, yet somehow the questions felt different. Before, I had approached the PM as a climate mystery. a geological puzzle involving carbon reservoirs, methane hydrates, volcanic activity, and ancient ecosystems. The focus had always been on identifying a natural mechanism capable of producing the observed effects. That approach remains scientifically valid, and it continues to guide much of the research today. But after reading Schmidt and Frank's paper, I began wondering whether there was another layer to the story, not an alternative explanation, but an alternative perspective. Because the Silurian hypothesis was never really about ancient civilizations, it was about recognition. It was about asking whether certain kinds of evidence might look the same regardless of what produced them. And once that possibility enters your mind, it becomes difficult to look at the PETM in exactly the same way. The first similarity that struck me was the carbon itself. During the PETM, an enormous quantity of biologically derived carbon entered the atmosphere. That much is clear. The fingerprint exists. The geological record is remarkably consistent. Scientists can measure the isotopic shift in sediments collected from multiple continents and oceans. The data is not ambiguous. Something released a staggering amount of carbon-12 rich material into Earth's climate system. What surprised me was how often modern discussions of industrial civilization involve precisely the same kind of signal. Today, we burn fossil fuels that originated from ancient biological matter. The result is a measurable isotopic change in the atmosphere. Future geologists, millions of years from now, would almost certainly detect that signal. They would see the carbon excursion. They would observe the atmospheric disruption. They would recognize that something unusual had happened. The fingerprint would survive. The question is whether they would know exactly what produced it. Suddenly, the PEM seemed less like an isolated anomaly and more like a thought experiment unfolding inside the geological record. Not because it proves anything, but because it demonstrates how certain signatures can persist long after their origins have disappeared. Then there was the issue of scale. The PTM involved a carbon release large enough to alter global climate. Temperatures rose across the planet, ocean chemistry changed, ecosystems experienced profound stress. Recovery required hundreds of thousands of years. These are not local effects. They are planetary effects. And once again, the comparison felt difficult to ignore. A sufficiently advanced industrial civilization would also generate planetary consequences. Climate systems respond to carbon regardless of where that carbon originates. The atmosphere does not care whether molecules come from volcanic activity, methane deposits, biological reservoirs, or industrial combustion. Carbon remains carbon. The climate responds accordingly. What survives in the geological record is the effect, not necessarily the cause. That realization became increasingly important because the Silurian hypothesis was forcing me to think like a future geologist. Imagine standing 50 million years in the future, looking backward at our present era. The cities are gone, the satellites are gone, the factories are gone, yet the atmospheric signal remains preserved in sediments. The carbon excursion remains visible. Ocean chemistry records the disturbance. Future researchers would know something happened. They might even reconstruct much of its environmental impact. But would they immediately conclude that a technological civilization caused it? Or would they spend decades debating natural mechanisms capable of producing the same signature? The more I considered that question, the more uncomfortable it became. Not because it suggested a hidden civilization in the past, but because it highlighted a limitation in interpretation. Evidence rarely arrives with labels attached. Rocks do not explain themselves. Sediments do not provide context. They preserve clues, not conclusions. And the PETM seemed to embody that principle perfectly. The fingerprint was clear. The source remained uncertain. Another similarity emerged when I looked at the unresolved carbon budget itself. Decades of research have narrowed possibilities, improved models, and refined estimates. Yet the discussion continues. There remains uncertainty regarding the precise combination of mechanisms responsible for the event. Again, this does not mean scientists have failed. Quite the opposite. It demonstrates how difficult it can be to reconstruct ancient events from incomplete records. But viewed through the lens of the Silurian hypothesis, the uncertainty acquired a new significance. If geology struggles to fully reconstruct a known natural event, How confidently could it identify an unknown type of event? The question lingered in my mind longer than I expected, because ultimately, the Silurian hypothesis does not challenge geology, it challenges assumptions. It reminds us that the geological record preserves consequences more reliably than causes. It records what happened, not always why it happened. And when I returned to the PM with that thought in mind, I began noticing something else. Nearly every discussion focused on explaining the fingerprint. Very few discussions focused on the possibility that the fingerprint itself might be teaching us something about the limits of interpretation. Perhaps that is why the hypothesis generated so much attention despite making no extraordinary claims. It exposed a blind spot, not in the data, but in the questions we ask about the data. The more I reflected on it, the more I found myself returning to a single idea. We know something happened 56 million years ago. The evidence is real. The fingerprint remains. The carbon entered the atmosphere. The climate changed. Oceans responded. Ecosystems suffered. Those facts are not in dispute. What remains uncertain is the exact chain of events that produced them. And that uncertainty matters because hidden within it lies a larger question, like one that extends far beyond the PEM itself. How many other events in Earth's history are preserved as fingerprints without identities? How many geological anomalies represent effects whose causes remain only partially understood? And perhaps most unsettling of all, how many times have we assumed we recognized a natural event when in reality we were only recognizing its consequences? I did not have answers to those questions. In truth, I still do not. But by now, the PETM had become something more than a climate mystery. It had become a mirror, a reminder that evidence survives unevenly, that time erases context, and that sometimes the most important question is not what happened, but whether we are asking the right question about what happened. And with that thought lingering in the back of my mind, I found myself turning toward another mystery, one far younger than the PETM, yet perhaps even more difficult to explain. A moment in Earth's history when the climate shifted suddenly, ecosystems vanished, and traces of catastrophe appeared across entire continents. A moment known today as the Younger Dryas. For a long time, I assumed the greatest mysteries in Earth's history must be the oldest ones. Events buried tens of millions of years in the past seemed naturally more difficult to understand than anything closer to our own time. After all, the further back we travel, the fewer clues survive. The geological record becomes fragmented, continents shift, mountains erode, oceans rewrite the surface of the planet. Yet the more I explored Earth's history, the more I discovered that age is not always the deciding factor. Sometimes a mystery can be surprisingly recent and still remain unresolved. Sometimes the evidence can be abundant, the timing can be relatively well known, and yet the central question persists. What happened? That question led me to a period known as the Younger Dryas, and the first time I encountered it, I immediately understood why it continues to provoke debate. Because unlike the PETM, which unfolded 56 million years ago, the Younger Dryas occurred only about 12,800 years ago. In geological terms, that is almost yesterday. Human beings were already present. Large mammals still roamed vast regions of the planet. The Ice Age was ending. The world was changing. And then something happened. To understand why the Younger Dryas is so unusual, we first need to imagine the world just before it began. For thousands of years, the Earth had been emerging from the grip of the last great ice age. Massive glaciers that once covered enormous portions of North America and Europe were retreating. Temperatures were rising. Ecosystems were recovering. Forests expanded into regions that had previously been dominated by ice and tundra. Life was adjusting to a warmer world. Everything seemed to be moving in one direction, toward warmth, toward stability, toward the climate we know today. The trend appeared clear. The Ice Age was ending. Then suddenly, it wasn't. That is what makes the Younger Dryas so extraordinary. Instead of continuing to warm, the climate reversed. In some regions, temperatures dropped dramatically within what may have been only a few decades. Imagine living through such a transformation. One generation experiences a warming world, expanding forests, melting ice, increasing abundance. The next generation finds itself confronting colder temperatures, harsher conditions, and environmental uncertainty. To modern observers, the shift almost feels impossible. Climate systems are often imagined as slow-moving processes unfolding across millennia. Yet the Younger Dryas demonstrates that under certain conditions, change can occur with astonishing speed. The geological record leaves little doubt that something dramatic happened. Ice cores extracted from Greenland preserve one of the clearest records. Layer after layer, year after year, ancient snow accumulated and compressed into ice. Trapped within that ice are tiny bubbles of ancient atmosphere, chemical snapshots of the past. When scientists analyzed those layers, they discovered evidence of an abrupt cooling event, unlike anything expected during the transition out of an ice age. Temperatures plunged, atmospheric conditions shifted, environmental systems responded rapidly. The signal appears not only in Greenland, but across multiple regions of the Northern Hemisphere. Once again, we encounter a fingerprint, a global signal, a disruption preserved in natural archives. And once again, the question becomes difficult to avoid. What caused it? At first glance, the answer might seem straightforward. Climate systems are complex. Ocean currents shift, ice melts, fresh water enters the oceans. Small changes can trigger larger consequences. For many years, one of the leading explanations involved the sudden release of meltwater from massive glacial lakes in North America. As glaciers retreated, enormous quantities of fresh water accumulated behind natural ice dams. If those dams failed, fresh water could flood into the North Atlantic. Such a flood might disrupt ocean circulation patterns, particularly the systems responsible for transporting heat northward. Less heat reaches the northern hemisphere, temperatures fall, and a cooling event begins. It is an elegant explanation, plausible, scientific, supported by evidence. Yet as I continued reading, I noticed something familiar. The story was not completely settled. Certain observations fit the model extremely well. Others remained difficult to reconcile. Some regions appeared to respond differently than expected. Certain environmental signals seemed unusually abrupt, and as researchers gathered more data, alternative possibilities began emerging. The debate became more complicated, more nuanced, more interesting. What fascinated me most was not the disagreement itself. Scientific disagreement is normal. It drives progress. What fascinated me was the persistence of the mystery. Here was an event that occurred relatively recently, an event recorded in ice cores, lake sediments, ocean deposits, and environmental records across multiple continents. Yet despite decades of investigation, researchers continued debating the precise trigger. The fingerprint was clear. The cause remained uncertain. That pattern felt strangely familiar. I found myself remembering the PTM, different event, different timescale, different evidence, yet the same underlying structure, a dramatic planetary change preserved in the geological record, accompanied by questions that refused to disappear. The deeper I explored the Younger Dryas, the more remarkable it seemed. Because this was not merely a climate fluctuation, entire ecosystems responded, animal populations shifted, human societies living at the end of the Ice Age faced environmental transformations that may have altered the course of history itself. The world changed, and it changed quickly. But perhaps the most unsettling aspect was how sudden it appears. The Earth was warming, the glaciers were retreating, the climate seemed headed towards stability. Then, almost without warning, the trend reversed. The sky itself seemed to change the direction of history. And somewhere inside that reversal, hidden among ice cores, sediments, and ancient environmental records, lies one of the most fascinating questions I have ever encountered. Not simply how the climate changed, but what was powerful enough to make it change so quickly. Because the deeper I looked into the evidence, the more I began encountering clues that pointed beyond ordinary climate explanations. Clues scattered across continents, clues embedded within ancient layers of Earth, clues that suggested some researchers were beginning to ask a far more dramatic question. What if something came from the sky? The deeper I looked into the Younger Dryas, the more I began noticing a pattern that felt strangely familiar. Once again, there was a climate shift. Once again, there was a fingerprint preserved in the geological record. And once again, there was a debate about what had caused it. But this time, the clues were different. Instead of carbon isotopes, researchers were examining tiny particles buried within a thin layer of sediment. Instead of asking where the carbon came from, they were asking how certain materials ended up appearing across enormous portions of the planet at roughly the same moment in time. What caught my attention first was not a grand theory, but a simple observation. Scientists working in different locations, often thousands of miles apart, kept finding unusual materials concentrated within the same narrow geological horizon. North America, Europe, parts of Asia, and regions of the Middle East, site after site seemed to reveal traces of something extraordinary. It was as if a particular moment in Earth's history had left behind a signature visible across multiple continents. And whenever I encounter that kind of pattern, I immediately become interested, because isolated discoveries can sometimes be coincidences. Global patterns rarely are. One of the most intriguing findings involved nanodiamonds. The name sounds almost futuristic, but the concept is surprisingly simple. Nanodiamonds are extremely tiny diamond structures, so small they can only be observed using specialized instruments. Under ordinary conditions, they do not form easily. Their creation often requires enormous pressures and temperatures, conditions associated with powerful impacts, explosions, or other extreme events. Researchers examining Younger Dryas boundary layers reported finding unusual concentrations of these microscopic diamonds. I remember reading those papers and wondering how such tiny objects could become so important. Yet the more I learned, the more fascinating they became. Because nanodiamonds are not simply rare minerals, they are potential indicators of extraordinary energy. They suggest that something capable of generating immense pressure may have occurred. The discovery alone did not prove anything. Science rarely works that way, but it added another clue to the growing collection. Then there was iridium. Of all the materials associated with impact events, iridium may be the most famous. Decades earlier, unusually high concentrations of iridium helped support the hypothesis that a massive asteroid contributed to the extinction of the dinosaurs. Iridium is relatively uncommon within Earth's crust, but more abundant in certain extraterrestrial materials. When researchers find unexpected iridium enrichments, they naturally pay attention. Once again, some Younger Dryas sites appeared to contain elevated concentrations, not always consistently, not without debate, but frequently enough to attract serious scientific interest. What struck me was not the individual evidence itself. Each clue could potentially have multiple explanations. What struck me was the accumulation: nanodiamonds, iridium, and then another curious material began appearing in the discussion: shocked quartz. The first time I encountered the term, I assumed it referred to ordinary quartz damaged by geological processes. The reality proved far more interesting. Shocked quartz forms when quartz crystals experience immense pressures typically associated with powerful impacts or nuclear scale explosions. Under a microscope, the crystals exhibit distinctive deformation features, tiny structures that act almost like scars, evidence that the mineral endured forces far beyond ordinary geological conditions. Once again, researchers reported finding shocked quartz associated with certain Younger Dryas boundary layers. Once again, debate followed. Some studies supported the observations, others challenged aspects of the interpretation, yet the pattern continued emerging, evidence suggestive of extreme energy concentrated within a remarkably narrow slice of time. And then there was charcoal. At first, charcoal seemed almost mundane compared to nanodiamonds and shocked quartz. After all, charcoal simply indicates fire. Fires occur naturally. Forests burn, lightning strikes, ecosystems recover. Yet what made the Younger Dryas charcoal evidence unusual was its scale. In numerous locations, researchers identified significant charcoal deposits suggesting widespread burning. Not local fires, not isolated events. Broad regions appeared to have experienced extensive biomass burning around the same period. Imagine standing at the end of the Ice Age watching vast landscapes ignite. Forests, grasslands, vegetation accumulated over centuries, consumed within a relatively short span of time. The image is difficult to ignore, especially when considered alongside the other clues: nanodiamonds, iridium, shocked quartz, charcoal. Individually, each observation invites questions. Together, they begin forming a pattern that some researchers interpreted in a dramatic way. The hypothesis became known as the Younger Dryas impact hypothesis. According to this idea, fragments of a comet or asteroid may have entered Earth's atmosphere approximately 12,800 years ago. Yet, instead of producing a single obvious crater, the object could have fragmented, creating multiple airbursts and impacts across large regions. The resulting energy might explain widespread fires, atmospheric disruption, environmental stress, and perhaps even the sudden climatic changes associated with the Younger Dryas. The hypothesis attracted enormous attention and equally enormous criticism. Some studies supported aspects of the evidence, others failed to replicate certain findings. New discoveries strengthened some arguments while raising additional questions. The debate continues even today. And that, strangely enough, was what fascinated me most, because once again, I found myself confronting a familiar pattern. The evidence existed, the fingerprints existed, the geological record preserved something unusual, yet the interpretation remained contested. Different researchers looked at the same clues and reached different conclusions. The data was real, but the story behind the data remained uncertain. As I read through years of papers, responses, rebuttals, and new discoveries, I found myself thinking less about impacts and more about evidence itself. Because regardless of which explanation ultimately proves correct, one fact remained impossible to ignore. Across multiple continents, researchers had identified a narrow geological layer associated with unusual materials, environmental disruption, and dramatic climatic change. Something happened. The fingerprint remained. The question was not whether the layer existed. The question was what created it. And the deeper I followed that question, the more I realized it was leading toward another mystery entirely. Because climate was not the only thing that changed around the beginning of the Younger Dryas. Entire ecosystems shifted. Species disappeared. And one of the most successful human cultures of the late Ice Age seemed to vanish from the archaeological record almost as suddenly as the climate itself. As I continued following the trail left behind by the Younger Dryas, I eventually arrived at a question that felt far more personal than isotope ratios, nanodiamonds, or climate models, because climate does not exist in isolation. When the environment changes, life changes with it. Animals migrate, ecosystems reorganize, human societies adapt or struggle to adapt. And around 12,800 years ago, something extraordinary seems to have happened across large parts of North America. Entire species disappeared. Ancient hunting cultures changed, landscapes transformed, and for a brief moment, it almost feels as though an entire world vanished. The first time I encountered the Clovis culture, I expected a straightforward archaeological story. Clovis people are among the most famous early inhabitants of North America. Named after distinctive stone tools first discovered near Clovis, New Mexico, they have occupied a central place in discussions of early human migration for decades. Their spear points are remarkably elegant, carefully crafted, and instantly recognizable to archaeologists. For many years, Clovis represented one of the earliest widely accepted cultures in the Americas. Their tools appear across vast regions of the continent, suggesting a highly successful and adaptable population. What fascinated me was not simply their presence, but their timing. Clovis culture flourished near the end of the Ice Age, precisely when the Younger Dryas was beginning. The overlap was difficult to ignore. Here was a population living during one of the most dramatic environmental transitions in recent geological history. A population surrounded by enormous animals that no longer exist. A population whose world would soon experience abrupt climatic instability. And then, quite suddenly, the archaeological record changes, not necessarily a complete disappearance, but a transformation significant enough to provoke ongoing debate. To understand why this matters, we need to step back and imagine the world Clovis people inhabited. North America at the end of the Ice Age looked very different from today. Vast grasslands stretched across enormous regions. Glaciers still lingered in the north, and roaming through these landscapes were creatures that seem almost mythical by modern standards. Mammoths, mastodons, Giant ground sloths, ancient camels, massive bison, saber-toothed cats, dire wolves. The continent supported an astonishing collection of megafauna, animals far larger than most species alive today. It was a world filled with giants. And then, many of those giants disappeared. The extinction of North America's megafauna remains one of the most fascinating mysteries in prehistoric archaeology. Within a relatively short period of time, dozens of large animal species vanished. Mammoths disappeared, mastodons disappeared, giant sloths disappeared. Entire branches of evolutionary history simply ended. The timing has been debated extensively, but the overlap with the Younger Dryas remains striking. Once again, I found myself confronting a familiar pattern: climate disruption, ecological transformation, sudden change. And the deeper I looked, the more difficult it became to separate these events from one another. Researchers have proposed multiple explanations for the megafaunal extinctions. Climate change is one candidate. As temperatures shifted and ecosystems reorganized, some species may have struggled to adapt. Human hunting represents another possibility. Expanding populations could have placed increasing pressure on vulnerable animal populations. Some scholars argue that a combination of both factors produced the observed results. Others suggest additional mechanisms may have contributed. The debate remains active today. But regardless of which explanation ultimately proves correct, one fact stands out. Around the onset of the Younger Dryas, something significant happened to the ecological fabric of North America, and Clovis culture appears directly within that transition. What intrigued me most was not merely the disappearance of animals, but the apparent synchronization of multiple changes. Environmental conditions shifted, megafauna declined, archaeological patterns changed. It was as though several different stories were unfolding simultaneously, all converging around the same moment in time. That convergence reminded me of the PETM, not because the events were similar, but because the structure of the mystery felt familiar. Multiple lines of evidence pointing toward a period of profound disruption, multiple fingerprints preserved in different records, multiple questions emerging from a single interval in history. I remember staring at maps showing Clovis sites across North America. Thousands of miles separated many of them. Different landscapes, different environments, different communities. Yet they all existed within a world undergoing extraordinary change. Imagine being alive during that period. For generations, your ancestors knew a particular landscape. They knew migration routes, seasonal cycles, animal behavior, predictable patterns that shape daily survival. Then conditions begin changing. Temperatures fluctuate, ecosystems shift, familiar animals become harder to find, entire species begin disappearing. The world your grandparents knew starts slipping away. It is difficult to know exactly how Clovis people experienced these transformations. Archaeology can reveal artifacts, not emotions. Yet it is impossible not to wonder. What did they see? What stories did they tell? Did they recognize that they were living through an environmental upheaval unlike anything previous generations had known? Or did the changes occur gradually enough that no single moment felt extraordinary until viewed thousands of years later? These questions linger because they touch something universal. The Younger Dryas is often discussed as a climate event, a geological event, an environmental event, but for the people who lived through it, if they noticed it at all, it would have been something much more immediate. It would have been a change in the world itself, a change in weather, food, migration patterns, survival, a transformation not measured in graphs or isotope ratios, but in daily life. And perhaps that is why the disappearance of the Clovis world continues to capture attention. Not because it provides definitive answers, but because it sits at the intersection of so many mysteries. Climate change, megafaunal extinction, human adaptation, environmental disruption, all converging within the same narrow window of time. The fingerprints remain, the timing remains. Yet the exact relationship between these events continues to provoke debate. And as I followed that trail deeper into the evidence, I found myself confronting an increasingly difficult question. If so many changes occurred at nearly the same moment, could they truly be unrelated? Or were they all responding to a single cause, a single event, something powerful enough to alter climate, reshape ecosystems, and change the course of human history all at once? That question would lead me toward one of the most controversial ideas in modern archaeology and toward a debate that shows no sign of ending anytime soon. By the time I reached this point in the Younger Dryas story, I found myself staring at two competing explanations, each supported by evidence, each criticized by experts, and neither capable of fully silencing the other. The deeper I looked, the more I realized that the real mystery was no longer simply what happened 12,800 years ago. The mystery was why, after decades of research, the debate remains so alive. Usually, scientific controversies fade as evidence accumulates. One explanation gradually proves more convincing, uncertainty shrinks, and consensus emerges. Yet the Younger Dryas seemed determined to resist that process. Again and again, new discoveries appeared, old assumptions were challenged, and the argument continued. And perhaps the best place to begin is with the explanation that most researchers consider the more conventional one, the meltwater hypothesis. At first glance, the idea is elegant. It does not require impacts from space, cosmic catastrophes, or extraordinary events. It relies on processes already known to occur within Earth's climate system. At the end of the last ice age, enormous glaciers covered vast regions of North America. As temperatures increased, those glaciers began melting. The meltwater accumulated in gigantic lakes trapped behind ice barriers. One of the most famous was Lake Agassiz, a freshwater body so immense that it dwarfed many modern lakes combined. Imagine standing on the shore of such a lake. You would not see the opposite side. It would resemble an inland sea. The sheer volume of water is difficult to comprehend. According to the hypothesis, one or more catastrophic drainage events released enormous quantities of fresh water into the North Atlantic. Ocean circulation depends on differences in temperature and salinity. Warm, salty water moves northward, cools, sinks, and helps drive the conveyor belt that redistributes heat across the planet. But fresh water changes that balance. Large enough quantities can disrupt circulation. If the conveyor weakens, less heat reaches northern regions. Temperatures fall, climate patterns shift, the Younger Dryas begins. The explanation is attractive because it relies on mechanisms we know exist. Freshwater influences ocean circulation. Ocean circulation influences climate. The chain of events appears plausible. Numerous studies support aspects of the model. Geological evidence suggests large glacial lakes existed. Evidence also indicates that substantial freshwater releases occurred during the deglaciation period. For many researchers, this remains the leading explanation. Yet as I continued reading, I noticed something familiar. The model explained much, but not necessarily everything. Certain observations remained difficult to reconcile. Some climate changes appeared exceptionally abrupt, some environmental signals seemed unusually intense, and perhaps most importantly, the meltwater hypothesis primarily explains climate. It does not automatically explain nanodiamonds, shocked quartz, elevated iridium, or widespread charcoal deposits. Those clues required additional interpretation, and that is where the second explanation enters the story, the Younger Dryas impact hypothesis. If the meltwater hypothesis represents gradual environmental disruption, the impact hypothesis represents sudden catastrophe. According to this idea, fragments of a comet or asteroid entered Earth's atmosphere approximately 12,800 years ago. Rather than producing a single enormous crater, the object may have fragmented before impact. Multiple airbursts, explosions, and impacts could have occurred across large regions. The resulting energy would be extraordinary. Forests could ignite, atmospheric dust could spread globally, climate systems could experience severe disruption, ecosystems could suffer widespread stress. Some researchers argue that such an event could potentially connect many of the puzzles associated with the Younger Dryas: the abrupt cooling, the widespread fires, the extinction pressures affecting megafauna, the unusual materials found in boundary layers. The appeal of the hypothesis is obvious. It offers a single dramatic mechanism capable of explaining multiple observations simultaneously. But dramatic explanations inevitably attract scrutiny. Critics quickly raised important questions. Where is the crater? Can the reported evidence be replicated consistently? Are nanodiamonds truly diagnostic of impact events? Could alternative geological processes produce similar signatures? Over the years, numerous studies challenged aspects of the hypothesis, yet other studies supported portions of the evidence. New sites were discovered. Additional analyses appeared. Some criticisms weakened particular claims, while new findings strengthened others. The result was not resolution, but persistence. The debate survived. What fascinated me was that both hypotheses seemed to reveal something important about the nature of scientific inquiry. The meltwater hypothesis demonstrates how complex climate systems can generate dramatic change without requiring extraordinary external triggers. The impact hypothesis reminds us that extraordinary external triggers do occur. After all, Earth has been struck by asteroids before. We know impacts happen. The extinction of the dinosaurs stands as a powerful reminder of that reality. Neither perspective is inherently unreasonable. Both are grounded in legitimate scientific questions, and that is why the debate continues. I remember reading papers from both sides late into the evening, trying to understand why consensus remained elusive. What struck me most was not the disagreement itself, but the quality of the evidence supporting different interpretations. Everyone agreed the Younger Dryas occurred. Everyone agreed the climate shifted dramatically. Everyone agreed the environmental record contains unusual signals. The disagreement centered on causation, not the fingerprint, but the source of the fingerprint. Once again, I found myself reminded of the different evidence, different timescale, different hypotheses, yet the same underlying challenge. Geological records preserve consequences with remarkable fidelity. Causes are often harder to reconstruct. The Earth remembers what happened. It is sometimes less clear about why it happened. And perhaps that is why the Younger Dryas remains so compelling. Because beneath the technical debates, beneath the isotope measurements, beneath the sediment cores and climate models, lies a deeper question. What happens when multiple mysteries converge at the same point in time? Abrupt climate change, megafaunal extinctions, cultural transitions, unusual geological signatures. Each clue may have its own explanation, or perhaps they are connected. The answer remains uncertain, and that uncertainty is precisely what makes the Younger Dryas so fascinating. 12,800 years later, the fingerprint remains, the arguments remain, the evidence remains, and despite decades of research, the question refuses to disappear. What happened when the sky changed the world? As I followed that question further, I eventually found myself standing before something even stranger, a structure that should not have existed, a monument built by people who supposedly lacked the knowledge, organization, and agricultural foundations necessary to create it, a place buried intentionally, forgotten for thousands of years, and then rediscovered in the modern era, a place known today as Göbekli Tepe. If the Younger Dryas left behind questions in ice, sediments, and climate records, then Göbekli Tepe left behind questions in stone. And of all the mysteries I encountered while exploring this period of history, few affected me quite like this one. Not because Göbekli Tepe proves anything extraordinary, but because it forces us to reconsider assumptions we rarely think about. Assumptions about civilization, about progress, and about what ancient people were supposedly capable of accomplishing. The first time I saw photographs of the site, I assumed it belonged to a familiar chapter of history. Massive stone pillars, carefully arranged enclosures, intricate carvings, monumental architecture. The structures looked impressive, sophisticated, deliberate. Naturally, I assumed they must have been built by an established civilization, a society with agriculture, as permanent settlements, specialized labor, and social organization complex enough to coordinate large construction projects. In other words, the same sequence we usually associate with the rise of civilization. First agriculture, then villages, then cities, then monuments. That is the story most of us learn. It feels logical. People settle down, food production creates surplus, populations grow, labor becomes specialized, and eventually large architectural projects emerge. For generations, this sequence seemed almost self-evident. Then Göbekli Tepe appeared, and suddenly the timeline became much less certain. Located in southeastern Turkey, the site consists of enormous circular and oval structures built from limestone pillars. Some pillars stand more than 5 meters tall, others weigh many tons. Many are decorated with detailed carvings of animals, foxes, snakes, birds, wild boars, and creatures that must have held symbolic importance for the people who created them. Even today, the craftsmanship is striking. But what truly transformed the discussion was not the architecture itself, it was the age. Radiocarbon dating suggests that the earliest phases of Göbekli Tepe were constructed around 11,500 years ago. Let that number settle in for a moment. 11,500 years ago. Before Stonehenge, before the Egyptian pyramids, before the earliest cities of Mesopotamia, before writing, before metalworking, before virtually every civilization traditionally described in history books. The implications are difficult to overstate, because according to the conventional sequence, monumental architecture should not appear this early. Agriculture itself was only beginning to emerge. Permanent urban societies did not yet exist. Humanity was supposedly transitioning out of a hunter-gatherer lifestyle. Yet somehow, people were quarrying, transporting, carving, and arranging multi-ton stone pillars on a scale that seemed impossible for their era. I remember reading archaeological descriptions of the site late one evening and finding myself repeatedly returning to the same question: how? Not in a mystical sense, not in a supernatural sense, simply in a practical sense. How did communities without cities, without wheeled vehicles, without draft animals, without written administration organize labor on this scale? The answer, according to many archaeologists, is that they did. Human beings are remarkably capable. Cooperation, planning, shared beliefs, and collective effort can achieve extraordinary things, and that explanation deserves serious respect. Yet even among researchers, Göbekli Tepe generated surprise because it appeared to reverse a sequence that had long been taken for granted. Instead of agriculture producing monuments, some scholars began wondering whether monuments help produce agriculture. It is a fascinating possibility. Imagine groups of hunter-gatherers gathering seasonally at a sacred site. Large numbers of people require large amounts of food. Feeding those gatherings creates pressure to manage resources more effectively. Over time, cultivation emerges. Agriculture follows. Settlements become permanent. Civilization grows around the needs created by ritual and cooperation. In this interpretation, the monument comes first. Civilization follows. That reversal changed everything. Suddenly, Göbekli Tepe was no longer simply an archaeological site. It became evidence that human history might be more complicated than previously assumed. The people who built it were not primitive. They were not passive survivors wandering through the remnants of the Ice Age. They possessed knowledge, organization, and motivation sufficient to create something monumental, something that required planning across years, perhaps generations. And that realization became even more intriguing when viewed alongside the Younger Dryas. The dates overlap remarkably closely. Göbekli Tepe emerges shortly after one of the most dramatic environmental transitions of the late Ice Age, a period marked by climatic instability, ecological change, and widespread transformation. The timing may be coincidental. Many archaeologists would caution against drawing direct connections. Yet the proximity remains difficult to ignore. Human communities were living through profound environmental change, and at roughly the same time, one of the most extraordinary construction projects of the prehistoric world appeared. I often find myself imagining the people who stood on that hill 11,500 years ago. They did not know they were building something that would survive into the modern age. They did not know archaeologists would one day excavate their work. They did not know future generations would debate its significance. They were simply carrying stones, carving animals, organizing labor, and creating something important enough to justify enormous effort. Whatever their reasons, the result endured. Long after the climate changed, long after entire species disappeared, long after countless stories were forgotten, the stones remained. And perhaps that is what fascinates me most about Göbekli Tepe. Not that it answers questions, but that it preserves them. It stands at the edge of recorded history. almost like a message from a world we barely understand, a world existing between the end of the Ice Age and the dawn of civilization, a world where monumental architecture appears before it should, where old assumptions begin to crack, and where the line between what we know and what we think we know becomes surprisingly difficult to see. And as I continued exploring the site, I discovered something even stranger. Because hidden among the pillars was a particular carving, a specific stone, that some researchers believe may preserve a memory of catastrophe itself, a stone that would become known as the vulture stone. Among all the discoveries at Göbekli Tepe, there is one particular pillar that seems to attract more attention than almost any other. Archaeologists know it as Pillar 43. Many enthusiasts know it by a more dramatic name, the Vulture Stone. And the first time I saw an image of it, I understood why it has inspired so much debate. Unlike a simple architectural feature, the pillar appears filled with symbols, birds, animals, abstract forms, figures arranged in ways that seem deliberate rather than decorative. At first glance, it looks like a piece of ancient art, but for some researchers, it may represent something more, a message, a memory, perhaps even an attempt to record an event that changed the world. Now, before we go any further, it is important to be careful. What follows is not established fact. It remains a hypothesis, one interpretation among several. Many archaeologists disagree with it. Others find it intriguing. The debate continues. But whether one accepts the interpretation or not, the story itself is fascinating because it illustrates how ancient stones can provoke entirely new questions about the past. The vulture stone contains a collection of carved figures. A large bird dominates part of the composition. Nearby are other animals, including what appear to be a scorpion, a snake, and additional creatures whose identities remain debated. Um, for years, these carvings were generally understood as symbolic or ritual imagery. That explanation remains entirely plausible. Ancient monuments often contain symbolic animals. Religious and cultural meanings frequently become difficult to reconstruct after thousands of years, yet a different interpretation eventually emerged. Some researchers suggested that the animals might represent constellations. In other words, the carvings could be encoding information about the sky. The idea initially sounded speculative to me. Human beings have always searched for patterns among the stars, and it is easy to project modern astronomical interpretations onto ancient art. Yet the more I read, the more I realized why the proposal attracted attention, because if the carvings truly corresponded to constellations, they might preserve a specific moment in time, a celestial timestamp, and that possibility changes everything. Astronomy possesses a remarkable property. The positions of stars change slowly over long periods due to a phenomenon known as precession. The Earth does not spin like a perfectly stable top. Its axis gradually shifts over thousands of years. As a result, the relationship between constellations and seasonal positions changes over time. This means that if an ancient monument genuinely encodes a particular arrangement of stars, it may be possible to estimate when that arrangement was visible. In essence, the sky becomes a clock. And according to one controversial interpretation, the carvings on Pillar 43 point toward a date astonishingly close to the beginning of the Younger Dryas, approximately 10,950 BCE. The first time I encountered that number, I immediately recognized its significance. It falls remarkably close to the period when climate conditions changed abruptly, when the Younger Dryas began, when megafauna declined, and when some researchers believe a catastrophic event may have occurred. The coincidence was difficult to ignore. Of course, coincidence alone proves nothing. History is filled with coincidences, yet the possibility remained intriguing. What if the people associated with Göbekli Tepe were preserving a memory? Not necessarily a scientific observation in the modern sense, but a cultural memory, a symbolic remembrance of something extraordinary. Imagine a world emerging from the end of the Ice Age. Imagine communities witnessing dramatic environmental changes, unusual celestial phenomena, or events so disruptive that they become embedded within stories passed from generation to generation. Over centuries, those stories might become rituals. Rituals might become monuments. Monuments might become stone carvings. By the time archaeologists uncover them thousands of years later, only fragments remain. The original meaning becomes elusive, yet traces survive. That possibility fascinated me because it connects directly to a theme that has appeared throughout this entire journey: the persistence of fingerprints. The Earth preserves fingerprints in carbon. Climate records preserve fingerprints in ice. Sediments preserve fingerprints of environmental change. And perhaps, just perhaps, human memory preserves fingerprints as well. Not through perfect records, but through symbols, myths, monuments, and stories. The vulture stone sits precisely at that intersection. Some researchers see astronomical encoding, others see ritual symbolism, some see evidence of ancient skywatching traditions. Others see patterns that may not have been intended by the builders at all. The disagreement itself is revealing, because regardless of which interpretation ultimately proves correct, the pillar reminds us how little we truly know about the minds of the people who created Göbekli Tepe. We can measure the age of the stones, we can analyze the carvings, we can reconstruct construction techniques, but understanding meaning is far more difficult. Meaning belongs to human experience, and human experience rarely survives intact across 11,000 years. Still, I could not help returning to the date, roughly 10,950 BCE, close to the onset of the Younger Dryas, close to a period associated with environmental upheaval and cultural transformation. The alignment may be meaningful, it may be coincidental, yet it continues to provoke discussion because it touches a deeper question. What exactly were the builders of Göbekli Tepe trying to remember? Were they merely creating sacred spaces? Were they encoding cosmological beliefs? Were they preserving observations of the heavens? Or were they attempting to record something that future generations would otherwise forget? I do not claim to know the answer. In truth, nobody does. But standing before the vulture stone, even through photographs and archaeological reports, I find myself experiencing the same feeling that emerged during the PETM and the Younger Dryas, a sense that the evidence is pointing towards something important while withholding the final piece needed to understand it. The fingerprint remains, the interpretation remains uncertain, and perhaps that uncertainty is precisely what makes the stone so compelling. Because whether the carvings depict constellations, myths, rituals, or memories, they remind us that ancient people were not passive observers of the world. They noticed the sky. They noticed change. They preserved meanings important enough to carve into stone. And as I continued exploring Göbekli Tepe, another mystery emerged, one that may be even stranger than the carvings themselves. Because at some point, for reasons still debated today, the builders made a decision that seems almost impossible to understand. They buried the site, deliberately, carefully, completely, as though they wanted the stones to survive, but disappear. Of all the mysteries surrounding Göbekli Tepe, there is one that continues to trouble me more than any carving, more than any astronomical interpretation, and even more than the extraordinary age of the site itself. It is a question so simple that it almost sounds absurd. Why did they bury it? Not abandon it, not allow it to collapse, not leave it exposed to the elements. They buried it, deliberately, carefully, methodically, for thousands of years. The great stone circles of Göbekli Tepe lay hidden beneath tons of earth and debris. The pillars remained standing, the carvings remained preserved, the structures survived because someone intentionally covered them. The first time I learned this, I assumed the burial must have occurred naturally. After all, ancient sites become buried all the time. Wind deposits sediment, floods reshape landscapes, vegetation gradually covers abandoned structures. Nature is remarkably efficient at hiding the past, but that is not what happened here. Archaeological evidence suggests the enclosures were intentionally filled, material was brought in, spaces were packed, entire structures disappeared beneath layers of fill. It was not the work of centuries of erosion. It was an act, a decision. And that decision raises one of the most fascinating questions in archaeology. Why would people invest enormous effort constructing monumental structures only to bury them afterward? The more I thought about it, the stranger it became. Building Göbekli Tepe required extraordinary labor. Massive limestone pillars had to be quarried, transported, shaped, and erected. Communities cooperated to create something unlike anything previously known from that period. The structures clearly mattered. They were not temporary shelters. They were not casual constructions. They represented significant investments of time, energy, and meaning. Then, after all of that effort, the builders covered them. Imagine constructing a cathedral, then carefully burying it beneath a hill. Imagine carving intricate artwork, only to hide it from view. The behavior feels counterintuitive, and yet that is exactly what appears to have happened. Archaeologists have proposed several explanations. One possibility is that the burial represented a ritual act. Sacred spaces often undergo cycles of creation, use, transformation, and closure. Perhaps covering the enclosures was part of a cultural tradition. Perhaps the structures fulfilled their purpose and were ceremonially retired. Another possibility is that changing social conditions made the site less important. Communities evolve, beliefs change, new practices emerge. What once held profound significance can gradually lose its central role. These explanations are reasonable. They fit patterns observed elsewhere in human history. Yet I cannot help feeling that something remains elusive, because the burial was not careless, it was not destructive. If the goal had been abandonment, people could simply have walked away. Time would have done the rest. Instead, they invested additional effort preserving the structures beneath protective layers of fill. That distinction matters. It suggests intention. It suggests concern. It suggests that whatever motivated the burial, preservation may have been part of the objective. And that is where my thoughts begin drifting toward more difficult questions. What exactly were they protecting? The pillars themselves, the carvings, the sacred meaning associated with the site, or perhaps something less tangible, a memory. Throughout this journey, we have repeatedly encountered the idea of fingerprints, geological fingerprints, climatic fingerprints, cultural fingerprints, traces left behind by events long after direct evidence has vanished. Göbekli Tepe feels different because here the fingerprints are not accidental. Human beings placed them deliberately into stone. They invested enormous effort creating symbols that would outlast them, and then, somehow, they ensured those symbols survived. It is tempting to imagine that they understood something we often forget, that memory is fragile. Stories change, generations pass, oral traditions evolve. Yet stone endures. If a community wished to preserve something across centuries, or even millennia, stone would be one of the most reliable mediums available. I sometimes wonder what it would feel like to stand among those pillars at the moment before burial began. Imagine the people gathered there. The carvings are still visible. The enclosures remain open to the sky. The site is alive with meaning. Then someone makes a decision. Earth begins filling the spaces. Slowly, carefully, the monuments disappear from sight. The process may have taken weeks, months, perhaps longer. Each basket of soil carried into the enclosure represented an act of concealment, or perhaps an act of preservation. The distinction is important. Concealment hides something from the present. Preservation protects something for the future. Which was it? The truth is that nobody knows, and that uncertainty creates room for speculation. Some people see evidence of catastrophe, suggesting the builders wished to protect sacred knowledge from turbulent times. Others propose entirely ritual explanations, emphasizing symbolism over survival. Many archaeologists remain cautious, preferring interpretations grounded in observable evidence. I understand that caution. Extraordinary claims require extraordinary evidence. Yet even the most conservative interpretation leaves us with a remarkable fact. Human beings intentionally buried one of the most extraordinary sites of the prehistoric world. That fact alone remains astonishing. Then there is the question that lingers longest in my mind. If they were preserving something, who were they preserving it for? Themselves, their descendants, future generations they would never meet. Every act of preservation contains an audience, someone imagined in the future who might eventually uncover what has been hidden. Libraries are preserved for readers. Monuments are preserved for observers. Messages are preserved for recipients. So who was the audience of Göbekli Tepe? Perhaps there was none. Perhaps the burial served purposes entirely unrelated to future discovery. Yet I find it difficult to dismiss the possibility that preservation itself carries a quiet form of hope, a hope that something important will endure, a hope that memory will survive, a hope that even if the builders disappear, the stones will remain. And in a strange way, that hope succeeded. 11,000 years later, we are still asking questions about their work. We are still studying their symbols. We are still wondering what they wanted us to remember. The structures vanished, yet survived. The builders disappeared, yet their questions remain. And as I reflected on that paradox, another mystery emerged from the shadows of deep history. Because if Göbekli Tepe preserves memories in stone, there is another monument that some believe preserves memories in its very shape. A monument standing thousands of miles away, weathered by time, surrounded by controversy, and perhaps connected to a world far older than we have been taught to imagine. The Great Sphinx. There are certain monuments that seem to belong not only to history, but to mystery itself. Long before I began reading scientific papers about climate change, isotope ratios, or the Younger Dryas, there was one structure that continually appeared whenever people discussed forgotten ages and lost chapters of the human story: the Great Sphinx of Giza. Even today, after centuries of study, it remains one of the most recognizable monuments on Earth. Millions of visitors have stood before it. Countless photographs have captured its image. Archaeologists have examined it, historians have debated it, and yet, despite all that attention, the Sphinx continues to provoke questions that refuse to disappear. Most scholars associate the monument with ancient Egypt's Old Kingdom, specifically the reign of Pharaoh Khafre around 2500 BCE. This remains the mainstream interpretation, supported by archaeological context and evidence linking the monument to the surrounding pyramid complex. But as I followed the theme of ancient memories, forgotten catastrophes, and the possibility that parts of history may be older than we assume, I eventually encountered another debate, not about who built the Sphinx, but about how old it might truly be. The discussion begins with erosion. At first glance, erosion sounds like a dry geological subject, yet in this case, it became one of the most controversial questions in archaeology. The body of the Sphinx was carved directly from limestone bedrock. Over thousands of years, wind, sand, temperature changes, and weathering gradually altered its surface. That much is expected. The Egyptian plateau is an environment shaped by desert conditions. But, but some researchers noticed something unusual. Certain weathering patterns appeared less consistent with wind-blown sand and more consistent with prolonged exposure to heavy rainfall. The first time I encountered this argument, I was skeptical. After all, Egypt today is famously arid. Rain is relatively rare, yet the geological observations themselves were intriguing. Some geologists argued that portions of the enclosure surrounding the Sphinx displayed vertical weathering patterns, rounded features, and erosion characteristics more typical of water flowing down exposed surfaces than sand moving horizontally across them. If that interpretation were correct, it raised a fascinating possibility. Significant rainfall would imply climatic conditions very different from modern Egypt, conditions associated with periods much earlier than the traditionally accepted age of the monument. Suddenly, the discussion shifted from architecture to climate history, because the Sahara has not always been a desert. There were times in the distant past when North Africa was greener, wetter, and far more hospitable. Lakes existed where desert stretches today. Grasslands supported wildlife. Rainfall patterns differed dramatically from modern conditions. If the erosion truly reflected prolonged water exposure, some researchers argued the original carving of the Sphinx could potentially date back thousands of years earlier than conventionally believed. It is important to emphasize that this remains highly controversial. Many Egyptologists reject the interpretation, arguing that alternative geological processes can account for the observed features. Others remain open to further investigation. The debate continues. Yet what fascinated me was not the conclusion, but the question itself. Once again, we encounter a fingerprint, this time not preserved in carbon or ice or sediment, but carved into stone, a fingerprint left by weather, climate, and time. And once again, interpretation becomes the central challenge. Then there is the second layer of the mystery, one that moves from geology to astronomy. the so-called Leo alignment. The idea emerged from observations about the orientation of the Sphinx and the movement of the stars across long periods of time. The Sphinx faces east toward the rising sun. That fact alone is not controversial. Ancient civilizations frequently aligned important monuments with celestial events. But according to some researchers, if we look far enough back into the past, approximately 10,500 BCE, the constellation Leo would have appeared near the eastern horizon during the spring equinox. The connection immediately captured public imagination. A lion-shaped monument facing the rising constellation of the lion. The symbolism seemed powerful, almost too powerful. The first time I encountered the theory, I understood both its appeal and its problems. On one hand, human beings have always paid close attention to the sky. Astronomy played central roles in agriculture, religion, navigation, and timekeeping. Alignments are not inherently unreasonable. On the other hand, proving intentionality is extraordinarily difficult. The sky contains countless possible alignments. Distinguishing meaningful design from coincidence requires caution. Yet, despite the controversy, the date itself caught my attention. Approximately 10,500 BCE, a period remarkably close to the end of the Ice Age, close to the Younger Dryas, close to the era that has repeatedly emerged throughout our investigation. Once again, I found myself confronting the same feeling. Not certainty, not proof, but curiosity. Why do so many of these discussions seem to converge around similar periods of time? Climate disruption, environmental transformation, Göbekli Tepe, and now theories regarding the Sphinx. Are these merely coincidences created by human pattern seeking? Perhaps. The possibility must always be considered. Yet the repetition remained difficult for me to ignore. What ultimately interests me about the Sphinx is not whether a particular theory proves correct. It is what the monument represents. The Sphinx sits at the boundary between known history and unanswered questions. It reminds us that even some of the most studied structures on Earth continue to generate debate. It reminds us that evidence can be interpreted in different ways. And most importantly, it reminds us that history is not a finished book. New discoveries continue to emerge. Old assumptions continue to be challenged. The deeper we look, the more complicated the past often becomes. As I reflected on the erosion debate, the astronomical alignments, and the possibility that certain chapters of human history may extend further back than traditionally assumed, I realized something important. The question is no longer whether individual theories are correct. The larger question is whether we have underestimated the depth of the human story itself. Because if monuments, myths, and memories truly preserve fragments of events stretching back to the end of the Ice Age, then perhaps history begins earlier than we imagine. Not necessarily in the way popular speculation suggests, but earlier nonetheless. And if that possibility contains even a grain of truth, then the next mystery becomes impossible to avoid. Because scattered across cultures around the world, preserved in stories separated by oceans and continents, exists another form of memory, not carved in stone, but carried through generations. Hundreds of traditions describing floods, destruction, survival, and worlds that vanished beneath rising waters. Memories that some believe may preserve echoes of a catastrophe humanity never completely forgot. As I followed the trail of ancient memories, from climate records to stone monuments to stories that seemed to echo across thousands of years, I eventually arrived at a place that felt almost unreal. A place that does not rise above the landscape like the pyramids, nor stand exposed beneath the sky like Göbekli Tepe. Instead, it disappears into the earth itself. Hidden beneath the plains of central Turkey lies one of the most extraordinary structures ever discovered, a city beneath the ground, a city known as Derinkuyu. The first time I saw a diagram of it, I assumed it had been exaggerated. Surely no ancient community would carve an entire settlement beneath the surface of the earth. Yet the evidence was undeniable. Tunnel after tunnel, chamber after chamber, descending deeper and deeper underground. The scale was astonishing. Derinkuyu reaches approximately 18 levels beneath the surface. Even today, only part of the city is accessible to visitors. Archaeologists believe significant portions remain unexplored. Standing at the entrance, one might never suspect what lies below. A modest opening in the landscape leads into a labyrinth capable of sheltering thousands of people, and that is what fascinated me most. Not that people lived underground, uh, but that they invested enormous effort creating a place where large populations could survive beneath the earth for extended periods of time. The city contains living quarters, storage rooms, kitchens, workshops, stables, ventilation shafts, wells, gathering areas, and even spaces interpreted as schools or religious rooms. Everything necessary for life appears to have been considered. This was not a temporary cave, it was a designed environment, a place built with purpose, a place built for survival. As I studied the layout, I found myself asking a question that seemed unavoidable. Survival from what? Historians and archaeologists have proposed practical explanations. Throughout history, communities faced invasions, warfare, raids, and political instability. Underground refuges offer protection. The thick rock provides security, narrow passages can be defended easily, massive stone doors could seal entrances. In many ways, Derinkuyu makes perfect sense as a defensive refuge. Yet, the deeper I looked, the more difficult it became to ignore the scale. This was not a single shelter. This was not a hidden room beneath a house. This was an entire subterranean world. Constructing it required extraordinary labor across generations. People removed vast quantities of rock. They engineered ventilation systems capable of supplying fresh air deep underground. They designed wells that remained accessible even during sieges. Every aspect suggests careful planning. Every aspect suggests preparation, and preparation always raises questions about perceived threats. I often imagine what it would feel like descending into the city for the first time. The sunlight fades, the air becomes cooler, narrow passages twist downward into darkness. Level after level extends beneath your feet. Eventually, the surface world feels very far away. There is something psychologically powerful about such a place. It conveys a sense of caution, perhaps even anxiety. Human beings generally build upward when they feel safe. They build downward when they feel vulnerable. That observation stayed with me, because throughout this journey, we have repeatedly encountered traces of disruption. Climate shifts, environmental upheaval, megafaunal extinctions, stories of catastrophe, memories preserved in stone. Derinkuyu introduced another possibility, memories preserved through architecture. Again, I am not suggesting a direct connection. The city itself is far younger than the Younger Dryas. Archaeologists generally date much of its development to later historical periods, yet the psychological question remains fascinating. Why do human societies repeatedly create structures designed to survive disaster? Why do cultures invest enormous resources preparing for worst-case scenarios? The answer is obvious on one level. Because disaster happens, floods happen, droughts happen, wars happen. Human history is filled with uncertainty. Yet places like Derinkuyu seem to embody something deeper. They reflect an awareness that the world can change suddenly, that safety is not permanent, that survival sometimes requires retreat. And perhaps that is why the city feels so compelling. It is not merely an engineering achievement. It is a monument to preparedness, a physical expression of a simple but powerful idea: someday, something may happen. Looking through photographs of the tunnels, I could not help noticing how self-contained the city appears. Food storage areas, water systems, ventilation networks. Everything seems designed to minimize dependence on the outside world. It almost resembles a lifeboat carved into stone, not floating on the ocean, but anchored beneath the earth itself. And that image lingered in my mind, because lifeboats exist for a reason. They are built not because catastrophe is certain, but because catastrophe is possible. The distinction matters. It shifts attention away from specific theories and toward a broader understanding of human behavior. Throughout history, people have remembered danger. They have anticipated danger. They have built structures to protect themselves from dangers both real and imagined. Derinkuyu stands as one of the most dramatic examples of that instinct. The city itself does not tell us exactly what its builders feared. The stones remain silent. The tunnels preserve function, not emotion. Yet the architecture speaks in its own way. It tells us that survival mattered. It tells us that security mattered. It tells us that someone believed refuge might one day become necessary. And perhaps that is why Derinkuyu feels connected to the larger story we have been following. Not because it proves an ancient catastrophe, but because it reveals something universal about memory. Catastrophes leave marks. Some marks appear in geology, some appear in myths, some appear in monuments, and some appear in the choices people make when designing places to endure uncertainty. The deeper I descended into the story of Derinkuyu, the more I realized that the city was not simply a refuge, it was a reminder that human beings rarely forget danger completely. Memories evolve, stories change, generations pass, yet certain fears endure. And as I emerged from those underground tunnels, another question began taking shape. If communities remembered danger strongly enough to build entire cities beneath the earth, what kinds of memories might survive in stories passed from generation to generation? What happens when the memory of catastrophe escapes architecture and enters myth? Because scattered across the world from one culture to another, there exists a story so widespread, so persistent, and so strangely consistent that some researchers believe it may preserve the memory of a world changing event humanity never fully forgot: the story of the Great Flood. After spending so much time exploring geological fingerprints, buried cities, ancient monuments, and the possibility that human beings preserve memories in unexpected ways, I eventually encountered a question that felt both simple and deeply unsettling. What if some memories survive not in stone, not in artifacts, not in sediment, but in stories? At first, the idea seemed almost impossible to test. Stories change, details evolve, generations forget, myths absorb symbolism, legends grow larger with every retelling. Surely oral traditions cannot preserve meaningful information across thousands of years. At least, that was my assumption. Then I began looking into flood traditions, and the deeper I looked, the harder it became to dismiss them entirely. The first thing that surprised me was the sheer number. Flood stories are not rare. They are not confined to a single culture, a single religion, or a single continent. Researchers have documented hundreds of traditions involving catastrophic floods. Some estimates identify more than 500 separate flood narratives distributed across cultures around the world: North America, South America, Europe, Africa, Asia, Australia, the Pacific Islands. Again and again, stories emerge describing overwhelming waters, destruction, survival, and renewal. The global distribution alone is remarkable. Yet, what truly caught my attention was not the quantity, but the similarities. The details vary, of course. Different cultures interpret events through different beliefs and traditions. Names change, characters change, symbolism changes. Yet beneath those differences, certain patterns appear with surprising frequency. A great flood arrives suddenly. Most people perish. A small group survives. Knowledge is preserved. The world changes. Humanity begins again. The first time I encountered a comparative study examining these narratives, I expected broad themes and vague parallels. Instead, I found recurring motifs appearing over and over, not universally, but often enough to provoke curiosity. Some stories describe warnings before the catastrophe. Others describe boats, mountains, elevated refuges, or chosen survivors. Many portray the flood not as an ordinary seasonal event, but as something extraordinary, something world altering. And once I noticed those patterns, I found them difficult to ignore. Consider the story preserved in the ancient Mesopotamian epic of Gilgamesh. Long before many later flood narratives were recorded, it described a devastating deluge, a chosen survivor, a vessel built for preservation, and a world transformed by water. Then there's the biblical account of Noah: different culture, different religious framework, yet strikingly familiar themes emerge. Travel farther east, and flood traditions appear in parts of India. Travel west, and flood stories appear among indigenous peoples of the Americas. Move across the Pacific, and similar motifs emerge among island cultures separated by enormous distances. The question naturally follows: why? One explanation is straightforward. Floods are common experiences. Human societies often develop near rivers, lakes, and coastlines. Flooding represents one of the most widespread natural disasters in history. Different cultures experiencing local floods could independently develop similar stories. That explanation is entirely reasonable and undoubtedly accounts for many traditions. Yet some researchers argue that it may not explain everything, because certain flood stories do not simply describe flooding, they describe catastrophe on a much larger scale. They describe worlds ending, civilizations disappearing, and humanity facing existential threats. Whether those descriptions reflect historical memories, symbolic narratives, or combinations of both remains an open question. But the possibility itself fascinated me. Throughout this journey, we have repeatedly encountered the theme of memory. Göbekli Tepe may preserve memory in stone. Geological records preserve memory in chemistry. Ice cores preserve memory in trapped air. Could myths preserve memory in narrative? Not perfect memory, certainly not literal transcripts of events, but echoes, fragments, distorted reflections of experiences so significant that communities carried them forward through generations. The idea becomes especially intriguing when viewed against the backdrop of the end of the Ice Age. Sea levels rose dramatically as glaciers melted. Vast coastal regions disappeared beneath advancing waters. Entire landscapes that once supported human populations now lie submerged. Imagine witnessing such transformations over multiple generations. Shorelines retreat, familiar lands vanish, islands separate, valleys become seas. To the people living through those changes, the world itself might seem to be drowning. Memories of those events could easily become woven into stories retold long after the original geography was forgotten. I often find myself imagining a community gathered around a fire thousands of years ago. The oldest members recount stories inherited from their grandparents, who heard them from their grandparents before them. The details shift slightly with each generation, yet the central memory remains. Water rose, people fled, some survived, the world changed. Over centuries, the story evolves. Over millennia, it becomes myth. Yet perhaps somewhere inside the myth, a fragment of reality persists. Not because the story remains historically precise, but because memory itself is remarkably resilient. That possibility does not prove that all flood stories describe a single event. The evidence simply does not support such certainty. Different cultures experience different histories. Different floods occurred at different times. The world is complex. Yet what continues to fascinate me is the persistence of the theme itself. 500 cultures separated by oceans, languages, and histories repeatedly return to the same image: water, catastrophe, survival, renewal. Why does that image endure so powerfully? Perhaps because floods are universal human experiences. Perhaps because water naturally symbolizes destruction and rebirth. Or perhaps hidden beneath layers of symbolism. Some stories preserve distant memories of environmental transformations so profound that they became impossible to forget. The deeper I explore these traditions, the more I realize that the exact answer may be less important than the question itself. Because whether the stories preserve history, symbolism, or some combination of both, they reveal something fundamental about human beings. We remember, we tell stories, we carry fragments of the past forward even when we no longer understand their origins. And that realization led me toward one final question. If memories can survive in myths, if fingerprints can survive in stone, and if traces of catastrophe can persist across thousands of years, then what exactly are we remembering? What event was significant enough to leave echoes in geology, archaeology, architecture, and stories all at once? And perhaps most importantly, are those echoes pointing towards something we have not yet fully understood? The more I explored ancient flood traditions, the more I found myself asking a question that seemed surprisingly simple. What if some of these stories were not remembering a single flood, but a world that gradually disappeared beneath rising seas? Not a sudden catastrophe witnessed in a single day, but a transformation unfolding across generations. A transformation so immense that it altered maps, erased landscapes, and forced entire communities to abandon places their ancestors had known for thousands of years. Because one of the most remarkable facts about the end of the last ice age is not how much the climate changed, but how much the coastline changed. Today, we take the shape of the continents for granted. We open maps, look at coastlines, and assume they have always been there. Yet 12,000 years ago, the world looked dramatically different. Vast amounts of water remained locked inside continental ice sheets. glaciers covered enormous portions of the northern hemisphere. As those glaciers melted, the oceans began rising, slowly on human timescales, but rapidly on geological ones. And by the time the process stabilized, global sea levels had risen approximately 120 meters. 120 meters. The number sounds abstract until you begin imagining its consequences. Entire coastal plains vanished. River valleys became estuaries. Islands formed where hills once stood. Regions that had supported human populations for countless generations disappeared beneath advancing water. The modern coastline is not ancient. In many places, it is surprisingly young. The first example that truly captured my imagination was Doggerland. Before I encountered the name, I had never heard of it. Yet once I learned about it, I found it difficult to stop thinking about. Doggerland was a vast region connecting what is now Britain to mainland Europe. During the Ice Age, it was not underwater. It was land, real land, forests, rivers, wetlands, grasslands, and ecosystems supporting both animals and human communities. If you had stood there 15,000 years ago, you would not have seen the North Sea. You would have seen a landscape stretching toward the horizon. People hunted there, traveled there, lived there. Entire generations called it home. Then the sea arrived, not all at once, but relentlessly. Century after century, the coastline retreated, valleys flooded, lowlands disappeared, communities adapted, moved, and adapted again. Eventually, Doggerland vanished beneath the water entirely. Today, fishermen occasionally recover evidence from the seabed: stone tools, animal remains, fragments of a lost landscape. The sea now covers a world that once existed in plain sight. Every time I think about Doggerland, I wonder what stories its inhabitants told. Imagine watching familiar hunting grounds disappear. Imagine explaining to your children that places your grandparents knew now lie beneath the ocean. Imagine generation after generation witnessing the shoreline move farther inland. Would such experiences become stories? Would they become legends? It seems almost inevitable. Then there is the Black Sea. Few debates illustrate the relationship between geology and memory quite like the Black Sea flood hypothesis. According to one controversial proposal, rising Mediterranean waters eventually breached a natural barrier and flooded into the Black Sea basin. The event may have transformed a smaller freshwater lake into the much larger sea we know today. The details remain debated. Researchers continue discussing the timing, scale, and speed of the process. Yet, regardless of the final conclusions, the broader reality remains striking. Significant environmental changes occurred throughout the region as sea levels rose after the Ice Age. Human communities living near those shorelines would have witnessed transformations difficult to imagine today. Entire settlements may have been abandoned. Landscapes familiar for generations may have disappeared beneath water. Once again, we encounter the same theme: memory, loss, adaptation. The deeper I explored these submerged landscapes, the more I realized how much of human history may now lie beneath the ocean. Modern archaeology focuses heavily on land because that is where we can easily excavate. Yet the coastlines occupied by many ancient communities no longer exist. They are underwater. The people who lived there were often drawn to rivers, estuaries, and productive coastal environments. Those locations offered food, transportation, and resources. They were natural places for human settlement, and they are precisely the places most vulnerable to rising seas. This realization changed the way I think about prehistory. We often imagine ancient humanity living in a static world, yet the reality may have been far more dynamic. Entire regions disappeared, maps changed, migration routes shifted, resources moved, human populations were forced to adapt repeatedly. Some communities succeeded, others vanished. The geological record preserves fragments of this transformation, but not its emotional impact. For that, we must rely on imagination. I sometimes picture a family standing on a hillside overlooking the sea. The shoreline lies farther inland than it did during their childhood. Places once visited regularly are now underwater. Elders speak of forests that no longer exist, valleys no longer visible, rivers swallowed by the ocean. To modern ears, such stories might sound mythical, yet they could originate from real experiences repeated across generations as coastlines changed. And perhaps that is why flood stories appear so frequently around the world. not because a single global flood occurred, but because countless communities witnessed their worlds being reshaped by water. The details differed, the locations differed, yet the emotional experience may have been remarkably similar: loss, displacement, survival, memory. Throughout this journey, we have followed fingerprints preserved in stone, carbon, ice, and myth. Now we encounter another kind of fingerprint, one preserved beneath the sea itself: Doggerland, ancient coastlines, submerged valleys, forgotten settlements, entire worlds hidden beneath modern oceans. And the more I thought about these drowned landscapes, the more I found myself asking a difficult question. If rising seas erased so much of the human past, how many chapters of our story remain hidden beneath the water? How many memories disappeared with those coastlines? And perhaps most intriguing of all, how much of what we call myth today may simply be history viewed through the lens of thousands of years of retelling? Because as I continued following that question, I discovered something even stranger: a pattern emerging not in geology, not in archaeology, but in memory itself. A pattern suggesting that some stories may survive far longer than we ever imagined possible. As we reach the end of this journey, I find myself returning to the same feeling that started it all: not certainty, not conviction, and certainly not proof. Just a question that has followed me through ancient rocks, buried cities, forgotten coastlines, mysterious monuments, climate catastrophes, and stories carried across thousands of years. A question that seems simple at first, yet becomes increasingly difficult to answer the deeper you look. What if we are not looking at the beginning of the story? When I first encountered the PETM, it seemed like a climate mystery. 56 million years ago, something released an enormous quantity of biologically derived carbon into the atmosphere. The fingerprint remains preserved in stone. The evidence is real. The climate changed, oceans acidified, ecosystems struggled. Yet after decades of research, questions remain. The fingerprint survives while the source remains uncertain. Then came the Silurian hypothesis, not as an answer, but as a challenge, a reminder that geological records preserve consequences more reliably than causes, a reminder that if something extraordinary happened deep in the past, the Earth might preserve its fingerprint while erasing almost everything else. Cities disappear, roads disappear, machines disappear, chemistry remains. The idea was unsettling, not because it proved anything, but because it exposed how little survives across millions of years. Then our attention shifted toward the Younger Dryas, a world emerging from the Ice Age, warming, stabilizing, and then suddenly reversing course. Temperatures fell, ecosystems changed, entire landscapes transformed. Something happened. The fingerprint remains in ice cores, sediments, and geological layers stretching across continents. Yet once again, the debate continues. Meltwater, impact, climate feedbacks. Perhaps one explanation is correct, perhaps several are. The evidence survives. The final answer remains elusive. Then there were the clues embedded within that mysterious layer: nanodiamonds, shocked quartz, iridium, charcoal, tiny fragments of a story written 12,800 years ago. Not proof of catastrophe, not proof of impact, but evidence of something unusual. Evidence that continues to provoke questions. Evidence that refuses to disappear. We followed those questions into the world of Clovis, where ancient hunting cultures witnessed dramatic environmental transformations. We followed them into debates about extinction, climate, and survival. Once again, a world changed. Once again, the fingerprints remained. And then we arrived at Göbekli Tepe, the monument that should not exist. Massive stone pillars rising from an age before cities, before writing, before conventional definitions of civilization. A place built by people we are still struggling to understand. A place that reversed assumptions about how civilization begins. A place that seemed to emerge from the shadows of the Younger Dryas itself. There we encountered Pillar 43, the vulture stone, a possible memory carved into limestone, a possible astronomical code, a possible coincidence, no certainty, only questions. Yet once again, questions that refused to die. We stood before the mystery of deliberate burial, an entire sacred complex hidden beneath the earth by the people who built it, not destroyed, preserved, not forgotten, concealed, waiting. Then came the Sphinx, weathered by time, surrounded by controversy, standing at the edge between accepted history and deeper possibilities. Rain erosion, astronomical alignments, ancient skies, ancient climates, ancient memories. Perhaps the conventional explanations are correct, perhaps not. The monument remains, the questions remain. And then we descended into Derinkuyu, 18 levels beneath the surface of the earth, a city carved into stone, a refuge, a sanctuary, a place designed for survival, whether built for invasion, uncertainty, or something else entirely. It revealed a truth about humanity. We remember danger, we prepare for danger, we build for survival. Finally, we followed the trail into mythology. More than 500 flood traditions spread across cultures separated by oceans, continents, and thousands of years. Stories of destruction, stories of survival, stories of worlds lost beneath water. Perhaps they emerged independently, perhaps they preserved fragments of real environmental changes. Perhaps both explanations contain truth. Then we looked toward the sea itself. 120 meters of sea level rise since the end of the Ice Age. Doggerland vanished beneath the North Sea. Ancient coastlines disappeared around the world. Entire landscapes drowned. Entire human worlds erased. The oceans rose and history sank with them. As I look back across all these clues, I realize something important. None of them prove the existence of a forgotten civilization. None of them prove that advanced societies existed before ours. None of them provide definitive answers. And that is precisely why they matter. Because science is not built upon certainty. Science is built upon questions. Honest questions. Difficult questions. Questions that remain open until evidence closes them. The deeper I traveled into this story, the less interested I became in extraordinary conclusions. What fascinated me instead was the persistence of mystery itself. Again and again, the Earth seemed to be telling the same story. Not a story about hidden civilizations, but a story about impermanence. Worlds disappear, coastlines vanish, climates change, species go extinct, cultures rise and fall, memories fragment, evidence survives unevenly, the past becomes harder to reconstruct than we imagine. Perhaps that is the real lesson hidden within all these fingerprints. Not that something extraordinary was definitely here before us, but that history is far deeper, far stranger, and far more fragile than we usually assume. We like to think of ourselves as the culmination of the story, the beginning of the future, the most advanced chapter ever written, and perhaps we are. But the Earth has existed for billions of years. Complex life has existed for hundreds of millions. Geological time stretches far beyond anything human beings can easily comprehend. In such vastness, certainty becomes difficult. Humility becomes necessary. And so, after everything we have explored, after the PETM, after the Younger Dryas, after Göbekli Tepe, after the flood stories, after the drowned coastlines, I arrive at a conclusion that is not really a conclusion at all. It is simply a confession. I do not know what was here before us. I do not know whether the fingerprints we have followed point toward forgotten civilizations, misunderstood natural events, or mysteries we have not yet learned how to recognize. I do not know whether ancient stories preserve history, symbolism, or both. I do not know whether we are looking at the beginning of the human story or merely the beginning of the chapter we can still remember. What I do know is that the Earth remembers more than we do. The rocks remember, the oceans remember, the ice remembers, the monuments remember, the myths remember. Fragments remain everywhere, waiting patiently beneath stone, beneath water, beneath time itself. And perhaps the most honest answer I can offer, after following all these clues, is also the simplest. Something happened. The fingerprints are real, the questions are real, and whatever was here before us, whether it was a civilization, a catastrophe, a forgotten world, or something we have not yet imagined, its shadow still lingers around us, hidden in plain sight, waiting for someone to ask the right question.